turbulent, and bursting with star formation. Unlike the grand spirals of today, these ancient galaxies are clumpy and irregular, yet they glow with extraordinary brightness, suggesting that massive stellar nurseries were active just a few 100 million years after the Big Bang. The light from these primordial galaxies has been stretched by the expansion of the universe, a process known as redshift. By analyzing this redshift, astronomers can estimate the distance and age of galaxies, essentially turning telescopes into time machines. What we see now is not what these galaxies are, but what they were eons ago, ghostly echoes from the deep cosmic past. Yet the mystery deepens. Some of these early galaxies appear too massive, too evolved, to fit within existing models of galaxy formation. They seem to defy the standard timeline, growing faster and earlier than expected. This forces scientists to reconsider aspects of cosmology itself. Perhaps dark matter played a more active role in early galactic evolution, or maybe the first stars formed in ways we do not yet understand. Indeed, these cosmic anomalies detected by Webb prompt deeper questions about our fundamental understanding of the universe's birth and evolution. One particularly intriguing puzzle is the rapid emergence of massive galaxies so soon after the universe's inception. Standard cosmological theories propose that galaxies grow gradually, merging and accreting matter over billions of years. Yet, Webb's observations challenge this notion, revealing giant galaxies formed remarkably early, only a few 100 million years post-Big Bang. This phenomenon suggests either the presence of an unknown mechanism driving accelerated galactic assembly or that the early universe had conditions conducive to a much faster growth of structure than previously believed. Astronomers speculate that these surprising observations might be explained by primordial clouds rich in gas and dark matter, denser and more massive than initially thought. Such conditions could dramatically speed star formation, leading to rapid galactic development. Another possibility involves the role of supermassive black holes at galactic cores. Early black holes could have acted as gravitational anchors, rapidly funneling matter inward, thus accelerating the growth of galactic structure and fueling intense periods of starburst activity. Furthermore, Webb has opened a new frontier in exploring galaxy collisions and mergers, events essential for understanding galactic evolution. When galaxies collide, their interactions stir gas clouds, triggering bursts of star formation that can illuminate whole regions. Observing infrared radiation, which penetrates dense cosmic dust clouds, JWST can capture these energetic events in exquisite detail, allowing researchers to observe galaxy mergers in unprecedented clarity. Such observations not only reshape our understanding of galaxy formation but also provide crucial insights into how our own Milky Way might have evolved. Scientists now believe that our galaxy experienced multiple mergers in its early history, a hypothesis supported by the complex stellar streams and populations found within its halo. By studying these distant collisions and mergers, astronomers can piece together the evolutionary paths that might have shaped galaxies closer to home. Adding another layer of complexity is the detection of organic molecules and chemical compounds within distant galaxies. Webb's powerful spectrometers have identified signatures of complex molecules in regions of active star formation, hinting at a chemical richness present from the earliest epochs. This discovery expands the potential timeline for cosmic chemical evolution, suggesting that the fundamental building blocks for life might have been widespread throughout the universe earlier than previously imagined. Webb's groundbreaking detection of these organic molecules, compounds rich in carbon, oxygen, nitrogen, and hydrogen, signifies more than just chemical complexity. It fundamentally reshapes our conception of cosmic habitability. The presence of these molecules in galaxies billions of years old hints that the chemistry necessary for life was established remarkably early in the universe. Such findings not only enrich our understanding of astrochemistry but also push scientists to explore the tantalizing possibility that life's molecular precursors are nearly ubiquitous, scattered across the cosmos long before planets like Earth ever existed. The telescope spectroscopic instruments, such as NIR-SPEC, near-infrared spectrograph, allow astronomers to dissect the chemical composition of distant galaxies with unprecedented precision. Observations reveal intricate molecular signatures, including polycyclic aromatic hydrocarbons, PAHs, often regarded as critical precursors to the formation of life-supporting environments. These complex organic molecules are found within vast, dense clouds of dust and gas, stellar nurseries illuminated by newborn stars. Their discovery in such ancient cosmic structures points to sophisticated chemical reactions taking place at surprisingly early stages in cosmic history. Moreover, Webb's sharp eyes have also unveiled detailed glimpses into the environments around active galactic nuclei, AGN, regions dominated by supermassive black holes consuming enormous amounts of matter. These AGN are cosmic powerhouses, emitting intense radiation capable of triggering or suppressing star formation across entire galaxies. By probing infrared emissions deep within these dynamic regions, astronomers can examine the complex interplay between supermassive black holes and their host galaxies. This relationship, known as AGN feedback, has profound implications. Black holes may either stimulate or halt star formation, shaping galactic evolution in ways we are only beginning to fully comprehend. Further complicating this cosmic puzzle, JWST has provided clearer views of galaxy halos, enormous, diffuse envelopes of gas, dust, and dark matter surrounding galaxies. Far larger than previously imagined, these halos serve as vast reservoirs of matter, feeding star formation and influencing galaxy morphology. Studies suggest that galactic halos could harbor significant amounts of previously undetected baryonic, ordinary, matter, potentially solving part of the long-standing mystery known as the missing baryon problem. This elusive matter, now slowly coming into view, may help explain discrepancies between theoretical models and observations of cosmic structures. In addition, JWST's deep field observations continue to expand our cosmic horizon, pushing the observable universe further back in time. Galaxies once considered the very limit of observational capabilities now appear clearly, revealing structures and star formation rates that challenge our current cosmological models. Particularly astonishing are the dense clusters and protoclusters of galaxies JWST has uncovered at extreme redshifts, well beyond any previously observed. These immense structures emerged incredibly early, suggesting that large-scale cosmic web formation, the interconnected filamentary network of matter permeating the universe, began sooner and progressed more rapidly than theoretical predictions anticipated. These findings necessitate refinements in cosmological simulations, including improved models of dark matter's gravitational role. The dark matter scaffolding, thought to underpin cosmic structure formation, must have been established swiftly and efficiently to facilitate the accelerated growth of these massive early clusters. Webb's data thus compel cosmologists to revisit assumptions about dark matter's distribution, density fluctuations, and interactions with ordinary matter in the early universe. Furthermore, JWST's capacity to peer through dust clouds illuminates previously obscured phases of galaxy evolution. Massive, dust-enshrouded galaxies, previously invisible to optical telescopes, now emerge vividly, revealing unexpectedly vigorous star formation hidden behind thick curtains of cosmic dust. The presence of these dust-obscured galaxies, dogs, at such ancient epochs implies that galaxies rapidly enriched themselves chemically, synthesizing heavy elements and dust much faster than expected. This rapid enrichment is likely due to prolific early generations of massive stars, whose explosive supernova deaths seeded their environments with heavy elements, fueling further star formation and planetary system development. The implications of this early chemical enrichment ripple outward toward understanding planetary formation processes themselves. Webb's findings suggest that exoplanetary systems could have formed far earlier than astronomers previously suspected, potentially even around the first generations of stars. Thus, the window for planetary, and perhaps biological, evolution in the cosmos has widened dramatically, shifting our understanding of when and how habitable conditions might have arisen in the universe. These discoveries carry deep philosophical implications as well. By revealing that the cosmic conditions necessary for life emerged swiftly and abundantly, JWST challenges us to reconsider our place in the universe, not as an improbable anomaly, but as a natural product of universal processes occurring across space and time. We begin to see our existence as intimately connected to the fundamental laws of physics and chemistry that govern the universe from its earliest moments, inviting profound reflections on the cosmic context of life itself. The journey of discovery led by Webb continues to unfold, promising not only new scientific breakthroughs but also a deeper comprehension of the universe's complexity, beauty, and potential for life. As humanity gazes ever further into the cosmic dawn, each new observation challenges established paradigms and enriches our cosmic perspective, compelling us toward a more profound understanding of our own origins within the vast tapestry of the universe. JWST's unprecedented ability to capture details across vast cosmological distances continues to reshape our comprehension of the very fabric of the universe. One particularly intriguing development arises from its observations of cosmic reionization, the epoch when the universe transitioned from opaque darkness into transparency, as the first stars and galaxies flooded their surroundings with energetic ultraviolet radiation. This process, occurring within roughly the first billion years after the Big Bang, stripped electrons from neutral hydrogen atoms, illuminating the cosmos and forever altering its structure and visibility. By precisely measuring the signatures of early galaxies, JWST has allowed astronomers to probe deep into this transformative era, reconstructing in detail how the universe awoke from its primordial darkness. Surprisingly, JWST data indicates that reionization began earlier and proceeded more rapidly than previous observations had suggested. The early galaxies responsible appear exceptionally luminous and productive, their populations of massive stars efficiently ionizing vast regions of intergalactic space. This suggests a fundamentally different composition and stellar structure for these primordial stars, often referred to as population 3 stars. These hypothetical first-generation stars, formed entirely from hydrogen and helium produced in the Big Bang, may have been extraordinarily massive, short-lived, and incredibly luminous, generating intense radiation that drastically influenced their surroundings. Although direct observations of population 3 stars remain elusive, Webb's detection of extremely distant galaxies provides indirect clues to their existence. The unusual brightness and high-energy output of these early galactic systems strongly imply they contain stellar populations different from any known today, fueling renewed theoretical modeling to predict their properties. Thus, JWST has opened new avenues to search for these elusive celestial ancestors, guiding astronomers toward more sophisticated interpretations of stellar evolution in the universe's infancy. In parallel, Webb's infrared instruments have offered new insights into the elusive nature of dark matter, the invisible substance accounting for roughly 85% of all matter in the universe. By precisely measuring the distribution and motion of visible matter within distant galaxies, astronomers can infer the gravitational presence and behavior of dark matter. Webb's observations reveal subtle but significant variations in galactic rotations and gravitational lensing effects that suggest new complexities in dark matter distribution. For instance, some early galaxies seem less influenced by dark matter than predicted by standard models, raising questions about how dark matter structures initially formed and evolved. Alternatively, these discrepancies could hint at entirely new physics, potentially requiring revisions or expansions to the fundamental cosmological model known as lambda-CDM, lambda-cold dark matter. Additionally, JWST's deep imaging capabilities have profoundly expanded our understanding of cosmic voids, vast, relatively empty regions in the cosmic web. Previously considered barren spaces between galaxy filaments, these voids have been shown to contain subtle yet intriguing structures, faint dwarf galaxies, and tenuous threads of gas previously invisible to astronomers. This discovery emphasizes the interconnectedness of all cosmic regions, highlighting how even seemingly empty spaces influence cosmic evolution and structure formation. Such findings demand a re-examination of cosmological models that incorporate a deeper understanding of the delicate interplay between voids and galaxy clusters. Simultaneously, JWST's refined view of stellar nurseries in galaxies closer to us, such as in the Orion Nebula or the Large Magellanic Cloud, has significantly enhanced our comprehension of star formation processes. Detailed infrared observations uncover intricate structures, protostellar disks, protoplanetary rings, bipolar jets streaming from young stars, and complex interactions between forming stars and their dusty environments. Webb's high-resolution imagery has even identified early planetary systems in formation, unveiling clues about the fundamental processes guiding planetary formation. Such insights allow scientists to piece together how solar systems similar to our own might form, evolve, and eventually harbor conditions suitable for life. Moreover, JWST observations have begun reshaping planetary science itself. Exoplanetary atmospheres, previously difficult to analyze thoroughly, are now being characterized with unprecedented clarity. Webb spectroscopy provides detailed atmospheric signatures of distant exoplanets, revealing water vapor, carbon dioxide, methane, and even trace gases that could indicate biological or geological activity. By examining worlds orbiting stars beyond our solar system, JWST not only informs our understanding of planetary habitability but also advances the search for extraterrestrial biosignatures, significantly progressing humanity's quest to discover life elsewhere in the cosmos. The philosophical implications of these findings extend further, offering a profoundly altered vision of humanity's place within the universe. Webb's revelations about the ubiquity of complex molecules, the accelerated emergence of galaxies, and the diverse conditions conducive to life foster an image of a cosmos richly capable of supporting complexity. Humanity's existence thus appears increasingly less isolated, reinforcing a view of life as an integral outcome of the cosmic evolutionary process rather than a mere anomaly. As JWST's observational campaign continues, each new revelation reshapes our cosmic narrative. Every image, spectrum, and data set not only deepens scientific understanding but also challenges humanity's imagination, compelling us to reconsider fundamental aspects of cosmology, planetary science, chemistry, and astrobiology. The discoveries of this telescope embody the essence of human curiosity and the endless pursuit of understanding, a quest pushing the boundaries of knowledge and redefining our cosmic identity. With JWST pushing the frontiers of observational cosmology, another exciting avenue of research emerges, understanding the influence of magnetic fields on cosmic structure formation. Although magnetic fields have long been known to exist within galaxies, their precise origin and role in early cosmic evolution remain deeply enigmatic. JWST's sensitive infrared instruments have begun to indirectly probe these ancient magnetic structures by observing polarized light scattered and emitted from distant, dust-rich galaxies. These subtle polarization signatures provide astronomers crucial clues about how magnetic fields influence gas dynamics, regulate star formation, and possibly shape the evolution of galaxies themselves. Indeed, recent analyses suggest that early galaxies possessed surprisingly well-organized magnetic fields, contrary to expectations that primordial magnetic fields would be weak and chaotic. Such well-structured magnetic fields could have facilitated the rapid collapse of gas clouds into stars and may even have influenced the rate and efficiency of early galaxy growth. This observation compels astrophysicists to explore new theoretical frameworks explaining how such magnetic fields were generated shortly after the Big Bang, perhaps through turbulence in the primordial plasma, cosmic inflation processes, or early star formation itself. Webb's discoveries thus initiate a fundamental shift in our understanding of magnetohydrodynamics at cosmological scales. Alongside these revelations, JWST's infrared eyes have shed new light on the phenomenon of gravitational lensing, nature's own cosmic magnifying glasses. Massive foreground galaxies or galaxy clusters warp the fabric of spacetime, bending and amplifying the light of more distant galaxies behind them. Webb has harnessed these gravitational lenses to peer even deeper into cosmic history, uncovering galaxies so faint and remote that they were entirely undetectable with previous telescopes. Such gravitational lensing not only expands observational horizons but also provides precise tests for Einstein's theory of general relativity on unprecedented cosmic scales, potentially uncovering subtle deviations from our current gravitational understanding. Gravitational lensing also grants astronomers rare opportunities to measure the masses and distributions of dark matter within galaxies and galaxy clusters. By analyzing the lensing distortions captured in JWST's detailed images, scientists can map dark matter's invisible architecture in 3 dimensions, revealing intricate filamentary structures that underpin cosmic evolution. These precise maps offer powerful new constraints on theories of dark matter, potentially illuminating the particle physics underlying this mysterious substance, thus bridging cosmology and fundamental physics. Furthermore, JWST's examination of stellar evolution at various cosmological epochs highlights profound differences in stellar populations across cosmic time. Early galaxies observed by Webb often contain dense clusters of massive, short-lived stars, differing significantly from the relatively calmer, more stable stellar populations of contemporary galaxies. Such observations provide new insights into the earliest stellar life cycles, including massive supernova explosions, gamma-ray bursts, and neutron star mergers, all events that profoundly influence chemical evolution and galactic environments. Intriguingly, Webb's observations extend even into the enigmatic phenomena surrounding stellar remnants, such as black holes, neutron stars, and white dwarfs, illuminating their roles in galaxy ecology. For instance, JWST's detailed spectroscopy has detected dust and heavy elements in the aftermath of neutron star collisions, events crucial for synthesizing elements heavier than iron, including gold and platinum. These findings enhance our understanding of nucleosynthesis, the cosmic alchemy responsible for the creation of elements, and provide vital clues about how essential elements for life became abundantly distributed across galaxies. On the planetary front, Webb's in-depth studies of exoplanetary atmospheres also raise exciting possibilities for future observations of Earth-like worlds. By detecting subtle atmospheric signatures, Webb has begun identifying potential biomarker molecules, chemicals whose presence could indicate biological processes. Methane, oxygen, ozone, and complex organic compounds detected in the atmospheres of distant planets could hint at biological activity or prebiotic chemistry, allowing astronomers to refine methods to search for extraterrestrial life in future exploratory missions. Moreover, JWST's exploration of icy moons and asteroids within our own solar system provides significant comparative data for astrobiology. Observations of Europa, Enceladus, Titan, and even distant Kuiper belt objects offer new insights into subsurface oceans, complex organic chemistry, and habitability conditions. These studies not only enhance our understanding of life's potential distribution within our planetary neighborhood but also contextualize broader searches for habitable worlds across the galaxy. Philosophically, these cumulative discoveries compel humanity to reconsider profound questions about our identity and purpose within a boundless universe. Webb's exploration of the cosmic frontier challenges the anthropocentric perspective, replacing it with a vision of life as an intrinsic and perhaps widespread phenomenon, governed by universal physical laws and chemical processes. This perspective inspires deep contemplation on the nature of consciousness, existence, and the remarkable continuity linking humanity to the farthest reaches of space and earliest epochs of cosmic history. Ultimately, the ongoing scientific quest driven by JWST represents humanity's profound and enduring desire for knowledge. With each new discovery, we come closer to comprehending the grand cosmic story, how galaxies are born, stars live and die, elements form, and life emerges. Each revelation not only expands our scientific horizons but also enriches our shared understanding of the universe's beauty, complexity, and interconnectedness. As JWST continues peering deeper into the cosmos, humanity moves steadily toward a greater cosmic awareness, forever reshaping our perception of the universe and our place within it. As JWST further sharpens humanity's cosmic vision, astronomers also grapple with profound new mysteries related to cosmic entropy and the ultimate fate of the universe. Webb's precise measurements of distant galaxies, galaxy clusters, and cosmic structures provide invaluable data for studying entropy, the gradual increase of disorder, on unprecedented cosmological scales. By examining the evolving distribution and energy dynamics of matter and radiation across vast stretches of spacetime, scientists can now refine their understanding of how entropy governs cosmic evolution, potentially unveiling deeper insights into the universe's irreversible journey toward eventual equilibrium, often called heat death. These detailed observations by JWST underscore the role entropy plays in cosmic phenomena, from galaxy formation to black hole growth and star formation efficiency. For example, the energetic outflows from active galactic nuclei and starburst galaxies distribute energy and matter into intergalactic space, significantly influencing local and cosmic entropy balances. JWST's infrared capabilities have enabled researchers to observe directly these energetic winds, revealing their widespread presence even in very early galaxies. This data informs new models of entropy-driven feedback processes, altering our understanding of the fundamental thermodynamic forces shaping the cosmos. Additionally, JWST's exploration of the most distant observable regions raises fascinating questions about cosmic isotropy, the assumption that the universe appears uniform in all directions. Deep-field observations sometimes reveal subtle anomalies or unexpected alignments among distant galactic structures, challenging the idea of uniformity at vast scales. Although these anomalies might initially appear minor, they carry potentially profound implications. Could they indicate undiscovered fundamental physics, relic effects from cosmic inflation, or perhaps even evidence of multidimensional cosmologies or interactions with parallel universes? Indeed, Webb's observations increasingly encourage cosmologists to test alternative theories, including variations on standard inflationary cosmology and multidimensional spacetime frameworks inspired by string theory and quantum gravity research. Such innovative theoretical developments aim to reconcile anomalies detected by JWST with our existing cosmological models, bridging observational astrophysics and theoretical physics in unprecedented collaboration. Moreover, JWST's detailed infrared imaging facilitates unique studies of cosmic dust evolution across time. Dust, comprising microscopic grains of silicates, carbon, and ice, plays a crucial role in star and planet formation, chemical evolution, and even the thermal balance of galaxies. Webb's observations reveal unexpected quantities of dust in galaxies formed soon after the Big Bang, indicating rapid cycles of dust creation and destruction. This rapid cycling demands new models of dust chemistry and supernova processes, prompting astronomers to reconsider how elements necessary for life were dispersed so efficiently throughout the early universe. Furthermore, by capturing detailed images of circumstellar disks, the birthplace of planets, JWST allows astronomers unprecedented glimpses into the formation processes of exoplanetary systems. Observations reveal complex patterns of dust and gas rings, spirals, and gaps, sculpted by forming planets or dynamic gravitational interactions. Such precise imaging of planet formation environments not only enriches our understanding of planetary origins but also provides invaluable context for interpreting our own solar system's development. In fact, JWST has begun exploring comets and asteroid populations within our solar system itself, studying their chemical compositions with unprecedented sensitivity. These celestial bodies serve as ancient cosmic archives, containing preserved materials from the solar system's earliest stages. By examining their molecular structures and isotopic signatures, astronomers gain direct insights into conditions existing billions of years ago, potentially illuminating the origins of Earth's oceans and even the ingredients of life itself. On a larger philosophical scale, JWST's discoveries encourage us to rethink our own cosmic narrative. The telescope's revelations about entropy, chemical complexity, and the universality of physical laws provide a powerful backdrop for contemplating human existence within this vast cosmos. These insights prompt reflections on interconnectedness, not only among cosmic processes but also between humanity and the universe that gave rise to it. The narrative revealed by JWST underscores a profound unity between the microscopic chemistry of life and the macroscopic evolution of galaxies, stars, and planets, binding all existence into a coherent cosmic story. Ultimately, as JWST continues its journey into the unknown, every observation becomes another step in humanity's quest to understand the cosmos more deeply, to decipher our origins, and perhaps to uncover hints of our shared cosmic destiny. The telescope, thus, is more than a scientific instrument. It embodies humanity's collective curiosity, our aspiration to explore, and our persistent pursuit of understanding. In exploring the farthest reaches of the universe, JWST enriches both scientific knowledge and human imagination, shaping how we perceive ourselves within the grand cosmic narrative that surrounds and defines us. Beyond cosmological mysteries and planetary origins, JWST's detailed observations are reshaping our understanding of cosmic time itself, an elusive dimension intertwined intricately with space, matter, and energy. By examining distant galaxies as they appeared billions of years ago, JWST effectively traverses the arrow of time, allowing humanity to witness stages of cosmic evolution otherwise forever lost. Each photon captured is a traveler from the distant past, offering insights into how cosmic structures evolved, how stars matured, and how galaxies emerged from primordial chaos into ordered forms. These observations reveal fascinating variations in galactic evolutionary pathways. Some distant galaxies observed by JWST evolved rapidly, forming stars at explosive rates, while others exhibited slower, more stable growth. This diversity suggests that cosmic evolution may follow multiple pathways influenced by subtle initial conditions, environmental factors, or variations in dark matter distribution. Understanding these different trajectories offers profound insights into the delicate interplay of gravity, dark matter, gas dynamics, and radiation that shapes galaxies across cosmic epochs. Moreover, JWST's refined views have exposed intricate, filamentary structures within galaxy clusters and intergalactic space, illuminating the web-like cosmic structure known as the cosmic web. These immense filamentary threads, comprised of gas, dark matter, and faint galaxies, connect distant galaxy clusters, channeling matter and energy across vast distances. JWST's sensitive infrared eyes reveal this structure more clearly than ever before, demonstrating that galaxies are not isolated islands but interconnected nodes within an extensive, dynamic network. Such discoveries emphasize the fundamentally relational nature of cosmic structures, suggesting that galactic evolution cannot be fully understood without considering their environment within the cosmic web. Additionally, JWST's observations increasingly challenge our notions of the boundary between life and non-life in the cosmos. The widespread detection of complex organic molecules and prebiotic chemistry in distant galaxies and planetary systems suggests that the universe is inherently predisposed toward complexity and perhaps even life itself. This chemical universality invites a paradigm shift, away from viewing life as an improbable cosmic accident, and toward recognizing it as an intrinsic consequence of universal physical and chemical laws. JWST thus encourages us to revisit fundamental biological and philosophical questions. Could life's emergence be inevitable, given suitable conditions? And if so, how widespread might life truly be across billions of galaxies? As JWST enriches our vision, it simultaneously reshapes our philosophical relationship with the universe. By capturing images of objects billions of years old, the telescope vividly underscores humanity's place in a vast temporal and spatial continuum. Seeing galaxies and stars from the earliest moments of cosmic history profoundly affects human understanding of time, existence, and our transient but meaningful place within an ever-changing universe. These images, by visualizing the deep past, invite humanity into a broader cosmic perspective, an invitation to see our history, present, and potential futures as intimately connected with the universal story. In this context, JWST's exploration goes beyond science. It touches upon humanity's collective consciousness and imagination. It invites us to perceive the universe not merely as something external to us, but as something that shaped us profoundly, chemically, biologically, and existentially. The cosmos is thus no longer distant and impersonal but intimately related to our origins, our nature, and our destiny. Finally, as JWST continues probing deeper cosmic frontiers, every observation expands our vision and comprehension of reality. The telescope embodies human curiosity at its finest, reflecting a ceaseless yearning to know more, see farther, and understand better. In unveiling the mysteries of distant galaxies, star formation, cosmic structure, entropy, dark matter, and potentially life itself, JWST does more than just reveal cosmic secrets, it enriches humanity's collective story, shaping our identity within the universe. As we peer ever deeper into space, we uncover the universe's wonders, ultimately discovering profound truths about ourselves along the way. The revelations provided by JWST continue to ripple through astrophysics, astronomy, astrobiology, and even fundamental physics, pushing the boundaries of what we previously thought possible. As Webb continues to peer into cosmic darkness, we are steadily unraveling a complex tapestry woven by gravitational interactions, energetic phenomena, magnetic fields, chemical evolution, and perhaps, life itself. Each discovery redefines how we perceive the universe, constantly reminding us that our understanding of reality is always evolving, driven by new data and fresh insights. A particularly fascinating frontier that JWST has begun to explore involves the study of transient cosmic events, such as gamma-ray bursts, GRBs, stellar explosions, supernovae, and kilonovae, the violent aftermath of neutron star collisions. By capturing the infrared signatures of these cataclysmic occurrences, JWST sheds new light on the mechanisms underlying some of the universe's most powerful phenomena. Gamma-ray bursts, for instance, represent some of the most energetic explosions in existence, occurring when massive stars collapse into black holes or neutron stars collide, producing extraordinary flashes of energy observable from billions of light-years away. JWST's infrared observations reveal previously hidden dust clouds and chemical enrichments accompanying these spectacular events, enabling scientists to decode the detailed physics behind such violent cosmic dramas. Further, JWST's detection of distant stellar explosions helps astronomers refine our understanding of cosmological distances. Supernovae, serving as standard candles, allow precise measurement of cosmic expansion rates, critically important for cosmology. Webb's high-resolution observations of these distant supernovae offer detailed insights into the expansion history of the universe, allowing astronomers to test and refine theories explaining mysterious phenomena like dark energy, the enigmatic force accelerating cosmic expansion. By providing clearer measurements of cosmic expansion rates, JWST may help resolve existing discrepancies, such as the Hubble tension, a puzzling mismatch between locally measured expansion rates and those inferred from cosmic microwave background observations. JWST also offers remarkable opportunities to test and refine theories of fundamental physics, including the nature of gravity itself. Observing gravitational lensing effects around massive galaxy clusters and black holes allows astronomers to conduct stringent tests of Einstein's general theory of relativity on unprecedented scales and precision. Some early JWST observations suggest subtle anomalies or deviations in gravitational lensing patterns, which, if confirmed, could point toward new gravitational physics or modified theories of gravity. These possibilities excite physicists, as even slight deviations from general relativity could imply entirely new fundamental physics, potentially leading to breakthroughs in quantum gravity or multidimensional theories. Additionally, Webb's sensitive instruments permit astronomers to peer into extreme cosmic environments, such as the vicinity of active galactic nuclei or the energetic accretion disks around black holes, with extraordinary clarity. By studying these environments, astronomers gain insights into the physics of matter under extreme gravity and intense radiation conditions, phenomena impossible to recreate on Earth. Such studies help illuminate fundamental questions about black holes, event horizons, and relativistic physics, deepening our understanding of cosmic phenomena at the edge of scientific knowledge. Moreover, JWST's ability to investigate chemical processes in both distant galaxies and local planetary systems provides fresh insights into cosmic chemistry and its implications for life's origins. Detailed observations of chemical interactions within protoplanetary disks, cometary nuclei, and interstellar clouds reveal complex molecules, amino acids, and prebiotic chemical processes far more widespread and efficient than previously imagined. The universality and rapidity of this chemical complexity suggest that life's chemical precursors are abundant and perhaps inevitable, dramatically expanding the potential for extraterrestrial habitability throughout our galaxy and beyond. Philosophically, JWST's findings encourage profound contemplation about humanity's place within the universe's expansive timeline. As we look billions of years back in cosmic history, witnessing galactic births and stellar deaths, we become keenly aware of our fleeting yet profoundly interconnected existence within the cosmic narrative. JWST's observations, capturing ancient photons that began their journey long before our solar system even formed, deepen our appreciation for our transient but meaningful existence, a brief moment within an unimaginably vast cosmic drama. Each discovery made by JWST thus enriches human knowledge not only scientifically but also existentially. As the telescope continues revealing the universe's secrets, we gain a deeper sense of wonder, humility, and interconnectedness. Humanity's exploration of the cosmos through JWST represents far more than scientific inquiry. It embodies our innate desire to understand ourselves and our place within the greater cosmos, continuously inspiring awe, curiosity, and contemplation about the profound mysteries that surround and sustain us. Ultimately, the James Webb Space Telescope stands as one of humanity's greatest achievements, a testament to our curiosity, ingenuity, and relentless pursuit of knowledge. Each observation peels back another layer of the cosmic mystery, revealing new puzzles and profound insights that challenge and refine our understanding of the universe. From distant galaxies and enigmatic black holes to the chemical complexity underpinning potential life, JWST's revelations bridge the microscopic and macroscopic realms, binding the story of atoms and molecules to the grand narrative of galaxies and stars. In this extraordinary journey, we have glimpsed not only the distant reaches of space but also our own origins reflected in cosmic processes. Webb's discoveries remind us of a profound interconnectedness, across space and time, matter and energy, life and the universe itself. Through its gaze, we recognize ourselves not merely as passive observers but as active participants in a cosmos still unfolding, continuously evolving toward greater complexity and wonder. As JWST continues exploring the depths of the universe, the discoveries it enables will continue to inspire humanity's collective imagination, challenge our fundamental assumptions, and deepen our appreciation for our existence. This powerful telescope has forever changed how we perceive our place in the cosmos, revealing a universe far richer, more dynamic, and more intricate than we ever dared to imagine. As we continue to look outward, guided by JWST's vision, we also look inward, better understanding who we are and our profound connection to the vast, beautiful, and mysterious universe we call home. NGC 1300 continues to captivate astronomers with its intricate structure and the secrets it holds about the mechanisms driving galactic evolution. Its well-defined barred structure is a focal point for studying the transport of gas and angular momentum. The bar acts as a cosmic conveyor belt, guiding interstellar material toward the central regions where it accumulates, igniting bursts of star formation. This process is further evidenced by the glowing, clumpy regions along its spiral arms, teeming with young, luminous stars. The nucleus of this galaxy presents another layer of intrigue. Observations have revealed a tightly bound nuclear ring encircling the core, composed of vibrant, star-forming regions. These rings are thought to arise from the complex interplay of gravitational forces within the bar and the spiral arms, funneling gas into specific regions where it collapses to form stars. This nuclear activity offers a glimpse into how galactic cores evolve and sustain themselves over time. NGC 1300's bar also plays a role in shaping the overall rotation curve of the galaxy. Unlike simple disk galaxies, barred spirals like this one exhibit unique rotational dynamics, with the bar influencing the motion of stars and gas across the galactic plane. By studying these dynamics, astronomers gain valuable insights into the role of gravity in dark matter in maintaining the stability of such systems. Dark matter, though invisible, is a critical component of NGC 1300 structure. The motion of stars and gas indicates the presence of a massive dark matter halo that extends far beyond the visible galaxy. This unseen matter is crucial for explaining why the galaxy's outer regions rotate as rapidly as they do without flying apart. Understanding the distribution of dark matter in galaxies like NGC 1300 provides important clues about the nature of this mysterious substance that dominates the universe. Another fascinating aspect of NGC 1300 is its environment. Situated in the constellation Eridanus, it resides in a region of the sky populated by other galaxies. These neighboring systems may exert subtle gravitational influences on NGC 1300, potentially shaping its structure over billions of years. Such interactions, whether through close encounters or long-range gravitational effects, are key to understanding how galaxies evolve within their cosmic neighborhoods. NGC 1300's size is another remarkable feature, with its diameter stretching approximately 110,000 light-years, making it comparable to our own Milky Way. This immense scale allows astronomers to study the galaxy as a microcosm of the larger universe, with processes such as star formation, gas dynamics, and the effects of dark matter all playing out within its borders. Each of these processes offers a piece of the puzzle for understanding the broader mechanisms governing galaxies throughout the cosmos. Observations of NGC 1300, particularly through high-resolution imaging from instruments like the Hubble Space Telescope, have revealed additional structural details. Faint outer regions of the galaxy, including extended spiral arms and possible tidal streams, suggest a dynamic history involving past interactions or mergers. These features provide clues about the galaxy's past and the forces that have shaped it into the majestic structure we observe today. Under continued observation, NGC 1300 reveals itself as an unparalleled example of galactic complexity and beauty. Its spiral arms, extending symmetrically from the bar, showcase intricate patterns of star-forming regions. These arms are not just visually stunning but also act as laboratories for studying the physical conditions that drive the birth of stars. They contain vast amounts of gas and dust, the raw materials for star formation, interspersed with clusters of young, hot stars that illuminate their surroundings. The galactic core of NGC 1300 also provides a unique opportunity to explore the behavior of supermassive black holes. Although no active galactic nucleus has been detected within this galaxy, the presence of a central black hole is strongly theorized based on models of galactic evolution. Such black holes are often integral to a galaxy's life cycle, influencing the movement of stars and gas in the inner regions and regulating star formation through their gravitational pull. Moreover, the bar structure itself acts as a mechanism for redistributing angular momentum within the galaxy. This redistribution can lead to the gradual migration of stars and gas, shaping the long-term evolution of the galaxy's morphology. NGC 1300's bar is particularly notable for its length and prominence, making it an ideal subject for studies focused on the lifespan and eventual dissolution of these features in spiral galaxies. High-resolution images of NGC 1300 have also uncovered faint stellar streams and other evidence of past interactions with smaller satellite galaxies. These features suggest that, like many other galaxies, NGC 1300 may have undergone episodes of minor mergers or gravitational encounters, which have contributed to its current form. Such interactions are key to understanding how galaxies grow and evolve over cosmic time, building up their mass and altering their structure. The environment surrounding NGC 1300 in the Eridanus constellation is also of great interest. This galaxy resides in a relatively sparse region compared to dense galaxy clusters, yet it remains close enough to other systems to experience their gravitational influence. This positioning provides astronomers with an opportunity to study how galaxies like NGC 1300 interact with their surroundings in less crowded environments, offering a contrast to the more dramatic interactions seen in galaxy clusters. The continued study of NGC 1300 has revealed an array of dynamic processes occurring within its structure. The galaxy's spiral arms, rich in both molecular gas and interstellar dust, are prime regions for the study of star formation. Within these arms, dense pockets of gas collapse under the influence of gravity, giving rise to massive star clusters that light up the surrounding material. These clusters, in turn, influence the surrounding environment through stellar winds and supernova explosions, creating a cycle of destruction and renewal that drives the galaxy's evolution. The bar of NGC 1300, stretching prominently across its center, serves as a channel for gas and dust, funneling this material toward the inner regions of the galaxy. This movement often results in the formation of a circumnuclear ring, a structure observed in many barred galaxies, including NGC 1300. Within this ring, star formation activity reaches a peak, producing a concentrated burst of new stars. These regions are of particular interest to astronomers, as they provide a window into the processes that fuel the central activity of galaxies and, potentially, their central black holes. Another fascinating aspect of NGC 1300 is its rotational dynamics. Unlike the rigid body rotation seen in smaller objects, galaxies like NGC 1300 exhibit differential rotation, where the inner regions rotate faster than the outer regions. This differential motion plays a critical role in shaping the spiral arms and maintaining their structure over time. By analyzing the rotation curves of NGC 1300, scientists can gain a better understanding of how mass is distributed within the galaxy, including the contribution of dark matter. The dark matter halo surrounding NGC 1300 is a key area of study. Although this component of the galaxy is invisible, its gravitational effects are evident in the motion of stars and gas. The halo extends well beyond the visible edges of the galaxy, influencing its overall stability and rotation. Understanding the distribution and behavior of dark matter in galaxies like NGC 1300 is essential for unraveling the mysteries of this elusive substance, which makes up a significant portion of the universe's mass. In addition to its internal dynamics, NGC 1300's interactions with its cosmic environment provide further insight into its history. Although it is not part of a dense galaxy cluster, the galaxy's proximity to other systems suggests that it may have experienced gravitational interactions in the past. These encounters can trigger tidal forces that reshape the galaxy's structure, inducing bursts of star formation or altering the distribution of stars and gas. The majestic barred spiral galaxy, sometimes referred to as this cosmic masterpiece, continues to fascinate astronomers with its intricate architecture and dynamic processes. Its grand spiral arms, radiating outward from the central bar, reveal an ongoing symphony of stellar birth and evolution. The vibrant regions of star formation within these arms are home to young, luminous stars that illuminate the surrounding gas and dust, creating striking contrasts against the darker background of interstellar space. This celestial wonders bar, a defining characteristic of many similar galaxies, serves as a gravitational conduit, guiding interstellar material toward its core. This process not only fuels the star-forming regions near the nucleus, but also sheds light on how such structures influence the long-term development of galactic morphology. Observing these mechanisms within this galactic marvel offers valuable insights into the broader behaviors of barred spiral galaxies. At the heart of this astronomical phenomenon lies a tightly wound nuclear ring, a region teeming with intense star formation. This feature, observed in numerous galaxies of its type, results from the gravitational effects of the bar channeling gas into the central regions. Such regions are hotspots for scientific investigation, revealing how material accumulates to create bursts of star formation and, possibly, feed the central supermassive black hole. This stellar island, spanning over 110,000 light-years, exhibits complex rotational dynamics. The stars and gas within the system move in distinct patterns, shaped by the bar and the unseen influence of its dark matter halo. These rotation patterns are key to understanding the distribution of mass within this galactic giant, shedding light on the hidden forces that maintain its structure and stability. Beyond its visible structure, this cosmic enigma resides in a relatively sparse region of space within the constellation Eridanus. While not part of a dense galaxy cluster, this luminous spiral likely interacts with its neighboring galaxies, influencing its evolution through subtle gravitational effects. Such interactions might have played a role in shaping the features we see today, including its prominent bar and well-defined spiral arms. This stellar titan, often called a barred spiral masterpiece, offers a stunning glimpse into the vast complexities of the universe. Its brilliant spiral arms, stretching gracefully from the central bar, seem almost frozen in time, a cosmic snapshot of galactic evolution. Yet, within these serene structures lies a chaotic dance of creation and destruction. Massive, hot stars form in dense regions of interstellar gas, only to end their lives in powerful supernova explosions, scattering heavy elements that fuel the next generation of stars. The heart of this galactic wonder, marked by a glowing nuclear ring, pulsates with energy. This ring, composed of densely packed star-forming regions, is like a galactic engine, continuously producing new stars. Scientists believe this activity is driven by the central bar, which acts like a gravitational funnel, directing gas into the inner core. This unique feature makes the galaxy a prime subject for understanding how barred spirals sustain star formation over billions of years. Interestingly, this cosmic marvel holds clues to the secrets of galactic longevity. Its bar is not a permanent feature. It is believed that bars evolve and eventually dissolve, reshaping the galaxy into a more classical spiral or elliptical form. Studying the bar in this galactic gem provides a rare opportunity to witness a transitional phase in galactic evolution. Researchers are particularly fascinated by how the bar redistributes angular momentum, affecting the orbits of stars and the flow of gas throughout the galaxy. The rotational dynamics of this spiral leviathan are equally captivating. Unlike solid objects, galaxies rotate in a way that defies simple explanations. The outer regions move more slowly than the inner regions, yet the presence of dark matter stabilizes this differential rotation. By studying the velocity curves of this astronomical icon, scientists are unraveling the influence of dark matter, which remains one of the greatest mysteries of modern astrophysics. This universal masterpiece is not isolated, it resides in a vast cosmic neighborhood within the Eridanus constellation. The faint whispers of past interactions can be seen in the subtle distortions of its outer arms and the faint trails of stars that may mark the remnants of smaller galaxies it has absorbed. These signs of cosmic encounters tell the story of a dynamic past, where gravitational forces sculpted the galaxy into its current form. Moreover, this spiral behemoth's size is breathtaking. It spans over 110,000 light-years, comparable to the Milky Way. This immense scale makes it a microcosm of the universe, offering a window into the processes that shape galaxies on a grand scale. Each observation of this celestial jewel adds another piece to the puzzle of how galaxies grow, change, and interact with the cosmos around them. This luminous galactic titan, often referred to as a cosmic labyrinth of stars and dust, captivates not only with its mesmerizing beauty but also with the stories it tells about the universe's grand design. The spiral arms of this celestial marvel, adorned with star-forming regions and glowing clusters, appear almost like rivers of light flowing outward from the galactic center. Each arm is a testament to the forces of gravity and motion, which sculpt the galaxy's intricate structure over billions of years. What makes this barred spiral phenomenon even more fascinating is its ability to balance chaos and order. The bar, stretching boldly across its core, is not merely a decorative feature but a dynamic powerhouse. This structure channels gas inward, creating a bustling hub of activity in the nucleus, while simultaneously affecting the spiral arms. This process shapes the galaxy into the perfect blend of symmetry and complexity, a hallmark of a mature barred spiral galaxy. Within the glowing center of this stellar colossus lies a nuclear ring that bursts with youthful stars. These concentrated regions of intense star formation are fueled by gas funneled into the core by the bar's gravitational influence. The interactions between the bar, the ring, and the surrounding spiral arms create a rich tapestry of activity that astronomers study to uncover the secrets of galactic metabolism, the rate at which galaxies consume gas and form stars. Beyond its striking visual features, this universal giant serves as a natural laboratory for studying dark matter. The unseen halo surrounding the galaxy provides the gravitational glue that holds its luminous components together. Without dark matter, the galaxy's outer arms would spin apart due to their incredible speeds. By examining the motion of stars and gas in this stellar titan, researchers are gaining deeper insights into the elusive substance that makes up most of the universe's mass. Adding to the intrigue of this celestial spectacle is its location within the constellation Eridanus, where it resides in a relatively quiet but not isolated patch of the cosmos. Surrounding galaxies leave subtle imprints on its structure, offering clues about past gravitational encounters. These interactions may have triggered bursts of star formation or subtle shifts in the galaxy's structure, contributing to the majestic form we see today. On the edges of this spiral marvel, faint trails and distortions hint at a dynamic history of mergers and accretions. These faint features are like cosmic fingerprints, telling a story of smaller galaxies that were consumed over millions of years. Such events are key to understanding how larger galaxies, including this barred spiral giant, grow and evolve through the cosmic ballet of interactions. The immense scale of this stellar masterpiece, often referred to as a galactic titan, is matched only by the complexity of the processes within it. Stretching over 110,000 light-years across, this barred spiral colossus is a vibrant ecosystem of stars, gas, and dark matter. Its spiral arms, like flowing rivers of starlight, are shaped by density waves that propagate through the galaxy, compressing gas and dust into regions where stars are born. These arms are more than just aesthetic features, they are dynamic sites of stellar evolution, where the interplay of gravity, motion, and matter creates dazzling patterns of light and energy. The bar, a defining feature of this cosmic marvel, serves as a critical driver of its internal dynamics. Extending through the galaxy's center, the bar acts like a gravitational engine, redistributing gas and stars. It funnels interstellar material into the core, feeding the central regions and potentially sustaining the activity of a supermassive black hole. Although this black hole remains hidden from direct observation, its presence is inferred from the galaxy's overall structure and the movement of stars near its nucleus. The nuclear ring within this celestial labyrinth is another highlight of its dynamic nature. This tightly packed region of active star formation is thought to be fueled by the bar's influence. The gravitational forces at play concentrate gas into the central regions, creating a fertile environment for the birth of massive, short-lived stars. These stars emit intense ultraviolet radiation, lighting up the surrounding gas and creating the glowing rings and patches observed in high-resolution images of the galaxy. This spiral wonder is also a fascinating subject for studying the influence of dark matter. While its luminous features are breathtaking, the hidden dark matter halo is what holds the galaxy together. Without this invisible mass, the outer regions of the galaxy would not rotate at the speeds observed. By analyzing the motion of stars and gas within the galaxy, scientists can map the distribution of dark matter, gaining critical insights into one of the universe's greatest mysteries. The cosmic history of this galactic marvel is written in its structure. Faint distortions in its outer arms and the presence of tidal streams suggest a history of interactions with smaller galaxies. These gravitational encounters leave behind subtle signatures, such as warped arms or faint trails of stars, which astronomers use to reconstruct the galaxy's past. Each merger or interaction adds to the richness of its structure, contributing to the majestic form we see today. Beyond its internal processes, this barred spiral galaxy is part of a larger cosmic tapestry. It resides in the Eridanus constellation, a region known for its diverse population of galaxies. Though it is not part of a dense galaxy cluster, its interactions with nearby systems influence its evolution. These interactions can trigger bursts of star formation or alter the distribution of stars and gas, shaping the galaxy over billions of years. The sheer scale and complexity of this spiral masterpiece make it an invaluable subject for astronomers. Its well-defined bar and spiral arms, active star-forming regions, and dynamic interactions with its surroundings offer a glimpse into the forces that shape galaxies across the universe. Every observation of this stellar titan adds another layer to our understanding of how galaxies like it evolve, interact, and adapt over cosmic time. This galactic marvel, often described as a cosmic colossus, offers an infinite reservoir of mysteries waiting to be unraveled. Its spiral arms, stretching like graceful bridges between the outer edges and the central bar, are home to some of the most dynamic and vibrant star-forming regions in the known universe. These arms are sculpted by density waves, large-scale gravitational phenomena that compress gas and dust as they propagate, triggering the formation of young, massive stars that illuminate the surrounding regions in hues of blue and white. The central bar of this universal masterpiece is not merely a static structure but a living, evolving feature. This bar acts as both a channel and a regulator, directing material inward while redistributing angular momentum outward. This constant flow of interstellar gas provides the fuel for the galaxy's star-forming regions and sustains the activity in its nuclear ring, a zone where the interplay between gravity and turbulence creates a bustling hub of stellar activity. Observing this process in such detail allows scientists to piece together how bars in galaxies like this one form, evolve, and eventually dissolve. One of the most intriguing aspects of this spiral titan lies in its hidden heart. While the central region appears bright and active, it may harbor a supermassive black hole, an enigmatic feature that could govern the dynamics of the galaxy's nucleus. Although there is no evidence of an actively feeding black hole in this barred spiral giant, its gravitational influence could subtly shape the motion of stars and gas within the inner regions. Studying this potential feature can reveal how such objects interact with their host galaxies over time, shaping their growth and evolution. The outer edges of this celestial giant also hold secrets about its past. Faint tidal streams and distorted structures suggest that it has experienced gravitational encounters with smaller galaxies or intergalactic clouds. These interactions may have left scars on its structure, subtly warping its arms or triggering bursts of star formation. These clues offer a window into the galaxy's evolutionary journey, showing how it has grown and adapted through mergers and interactions over billions of years. In addition to its internal features, this stellar giant's location within the constellation Eridanus places it in a fascinating cosmic neighborhood. Surrounded by a sparse yet diverse collection of galaxies, it is part of a dynamic environment that influences its behavior. Gravitational interactions with neighboring systems, even at great distances, can affect the shape of its spiral arms, the distribution of its stars, and the rate of star formation. This cosmic interconnectedness illustrates how galaxies are not isolated entities but are deeply intertwined with their environments. The study of this galactic masterpiece also extends to the unseen components that govern its dynamics. The role of dark matter, an invisible substance that permeates the universe, is especially significant in this barred spiral galaxy. Without the stabilizing influence of a massive dark matter halo, the galaxy's outer regions would not be able to maintain their rapid rotation. By analyzing the motion of stars and gas in the galaxy, astronomers can map the distribution of this mysterious substance and better understand its role in shaping the universe. This cosmic jewel's size alone is awe-inspiring. Spanning over 110,000 light-years, it rivals the Milky Way in scale and complexity. Its grand structure, from the luminous central bar to the sweeping spiral arms, serves as a natural laboratory for studying the processes that drive galactic evolution. Every observation of this spiral giant reveals new layers of complexity, helping scientists answer fundamental questions about the origins and fate of galaxies across the cosmos. This galactic titan, a sprawling cosmic tapestry of stars, gas, and mystery, is a playground for astronomers seeking to understand the forces that shape the universe. Its spiral arms, glowing with the light of newly formed stars, tell the tale of an ongoing cosmic ballet. These arms, rich with molecular gas and interstellar dust, are not static, they constantly churn and evolve, shaped by density waves that ripple through the galaxy. As these waves compress the gas, they create stellar nurseries where stars of all sizes are born, illuminating the galaxy like scattered jewels. The central bar of this celestial masterpiece is a dynamic and transformative feature. Acting as a galactic highway, it channels gas and dust inward, fueling the active core and potentially feeding the supermassive black hole thought to reside at the heart of the galaxy. The bar's gravitational influence also orchestrates the flow of material in the spiral arms, ensuring the galaxy maintains its symmetrical beauty. The sheer scale of this bar, stretching tens of thousands of light-years, makes it a dominant and mesmerizing feature, a bridge between the galactic core and its sprawling outskirts. At the very heart of this barred spiral giant lies a nuclear ring, a glowing, active hub of star formation that serves as a cosmic engine. This ring is where gravity and turbulence collide, concentrating vast amounts of gas into regions dense enough to ignite the birth of stars. The stars in this region are often young and massive, their intense radiation lighting up the surrounding gas clouds and creating a spectacle visible across millions of light-years. Observing this region helps astronomers understand the mechanisms behind intense starbursts and the life cycles of galaxies. Beyond its striking visible features, this galaxy holds a secret, the hidden realm of dark matter. While its stars and gas form the visible structure, they are merely the tip of the iceberg. Encasing this spiral beauty is a massive halo of dark matter, invisible to telescopes but essential for the galaxy's existence. This dark matter provides the gravitational glue that holds the galaxy together, preventing its outer edges from flying apart despite their rapid rotation. Studying the motion of stars and gas within the galaxy allows astronomers to map the distribution of this mysterious substance and explore its role in shaping cosmic structures. But this barred spiral isn't just a solitary wonder, it is part of a larger cosmic web. Its location in the constellation Eridanus places it in a sparsely populated region of the universe, yet it is not alone. Neighboring galaxies, some visible and others faintly detectable, interact with this galactic giant through gravitational forces. These interactions, whether past or present, leave subtle imprints on its structure, from distorted spiral arms to faint streams of stars that hint at ancient mergers. These clues offer a glimpse into the galaxy's dynamic past, a history written in the stars themselves. On the fringes of this cosmic giant, faint distortions in the spiral arms and wisps of tidal debris tell the story of a galaxy shaped by time and interaction. These remnants are the echoes of encounters with smaller galaxies, events that added mass to this spiral titan and contributed to its stunning complexity. Such mergers and accretions are common in the universe, illustrating the interconnectedness of galaxies and their shared evolutionary journeys. This barred spiral marvel is more than just a visual spectacle, it is a cosmic laboratory where the forces of gravity, motion, and energy come together in a delicate balance. Its intricate structure, from the glowing core to the sweeping arms, provides astronomers with invaluable insights into the mechanics of galactic evolution. Every star, every stream of gas, and every faint tidal remnant is a piece of a puzzle that tells the story of how galaxies like this one grow, adapt, and thrive in the ever-changing universe. This galactic titan, sometimes called a celestial symphony of light and motion, continues to amaze with its endless layers of complexity. Its sweeping spiral arms, sprawling outward like vast bridges through the void, are not only beautiful but essential to understanding how galaxies like it evolve. These arms are the sites of constant transformation, where the raw ingredients of the cosmos, gas, dust, and dark matter, combine to create new generations of stars. The interplay between gravity and motion within these arms results in an ever-changing cosmic dance that has persisted for billions of years. At the core of this spiral giant, the bar serves as a mechanism of cosmic engineering. This elongated structure is not just a static feature but a living, dynamic force within the galaxy. It acts as a gravitational conveyor belt, pulling material inward toward the central regions. This inflow of gas feeds the nuclear ring, a zone of intense star formation near the galaxy's center. Here, massive stars are born in rapid succession, their short lives punctuated by brilliant supernova explosions that enrich the surrounding gas with heavy elements. These elements will eventually form the building blocks of planets, moons, and possibly even life in distant star systems. The nuclear ring, glowing like a halo around the galaxy's heart, is one of its most fascinating features. It is a region where the forces of compression and turbulence collide, creating perfect conditions for the rapid birth of stars. Observing this process in such detail provides astronomers with a rare opportunity to study the mechanisms behind galactic starbursts, moments of intense star formation that shape the character of a galaxy over time. In this ring, the interplay between gravity and gas density creates a self-sustaining cycle of stellar creation and renewal. Beneath the visible beauty of this spiral masterpiece lies the invisible hand of dark matter. Encasing the galaxy is a massive dark matter halo that plays a critical role in its evolution. While this dark matter cannot be seen, its effects are profound, shaping the rotation curves of the galaxy and holding its luminous components together. Without the stabilizing influence of dark matter, the galaxy's delicate structure would unravel, and its outer arms would spin apart into the cosmic void. The study of this hidden component provides a window into one of the universe's greatest mysteries, the nature of the unseen matter that dominates its mass. The outer regions of this galactic marvel tell another story, one of cosmic interactions and ancient collisions. Faint distortions in its spiral arms and barely visible tidal streams suggest a history of encounters with smaller galaxies. These interactions, though subtle, have left permanent marks on the galaxy's structure, warping its outer edges and possibly triggering bursts of star formation in the past. Each of these encounters is like a chapter in the galaxy's life story, a record of how it has grown and adapted over billions of years. This barred spiral beauty resides in a relatively quiet part of the universe, within the constellation Eridanus. However, its cosmic neighborhood is not without influence. Gravitational forces from nearby galaxies, even those far removed, can subtly affect its shape and motion. These interactions remind us that no galaxy exists in isolation, instead, each one is part of a larger cosmic web, constantly influenced by its surroundings. The sheer size of this galactic wonder, spanning over 110,000 light-years, makes it an awe-inspiring subject for study. Its scale, comparable to that of the Milky Way, allows scientists to investigate processes that occur on both local and cosmic levels. From the tiniest star-forming regions within its arms to the grand sweep of its dark matter halo, every aspect of this galaxy contributes to our understanding of the universe. This cosmic titan is not just a static entity frozen in time, it is a living system, constantly changing and evolving. The cycles of star formation, the movement of gas through its spiral arms, and the gravitational interactions with its surroundings all demonstrate the dynamic nature of galaxies. Each observation of this barred spiral masterpiece adds a new piece to the puzzle of how galaxies like it form, grow, and thrive over the lifetime of the universe. When compared to other galaxies, this barred spiral giant stands out as an exemplar of complexity and harmony in galactic evolution. Unlike the simpler elliptical galaxies or irregular systems scattered across the cosmos, this galactic masterpiece showcases the intricate dynamics of a well-developed spiral galaxy with a central bar. These characteristics place it in a class of galaxies that serve as essential models for understanding how structure, motion, and energy interact over billions of years. One fascinating comparison can be drawn between this cosmic giant and our own Milky Way galaxy, which also features a central bar and sprawling spiral arms. While both galaxies share many structural similarities, such as the presence of star-forming regions and a likely supermassive black hole at their cores, each exhibits unique variations that make them valuable for study. For instance, the bar in this galactic titan is particularly prominent, suggesting it might be at a later stage in its evolutionary life cycle compared to the Milky Way. This raises questions about the lifespan of bars in spiral galaxies and their role in shaping long-term galactic dynamics. Another intriguing aspect is how this barred spiral compares to galaxies without bars. Spiral galaxies lacking bars tend to distribute gas and stars more evenly, while those with bars, like this one, create a more directed flow of material toward the core. This difference significantly impacts star formation and the growth of central supermassive black holes. In this barred beauty, the bar acts almost like a cosmic engine, driving material inward and fueling the intense activity observed in its nuclear ring. By studying these contrasts, astronomers can better understand the various pathways galaxies take as they evolve. This spiral wonder is also an excellent example of a grand design galaxy, a term used to describe systems with highly symmetrical and well-defined spiral arms. Such galaxies are thought to be influenced by large-scale density waves, which create the stunning patterns we observe. In contrast, flocculent spiral galaxies have less organized and patchy arms, making them appear more chaotic. The symmetrical nature of this galaxy's arms suggests that it has experienced relatively stable conditions, allowing these density waves to shape its structure over time. However, faint tidal distortions hint that even this seemingly serene giant has a dynamic past filled with interactions and changes. The broader cosmic web surrounding this galactic titan also plays a crucial role in its evolution. Unlike galaxies located in dense clusters, where interactions are frequent and often violent, this spiral resides in a less crowded region, allowing it to maintain its graceful structure. Yet, even in this quieter setting, gravitational interactions with neighboring systems have likely influenced its form. These subtle encounters, often stretching over millions of years, contribute to the galaxy's story, shaping its spiral arms, triggering star formation, and possibly altering the trajectory of its bar. Interestingly, this barred spiral galaxy is also a key player in the study of galactic feedback processes. Feedback refers to how energy and matter expelled by stars and black holes impact the surrounding environment. In the case of this galaxy, stellar winds, supernova explosions, and potentially even outflows from its central black hole interact with the surrounding gas, regulating star formation. This delicate balance ensures the galaxy doesn't burn through its gas too quickly, allowing it to sustain star formation over billions of years. The study of this cosmic marvel has also shed light on the fate of galaxies with bars. While the bar is a prominent feature now, it is not permanent. Over time, the redistribution of angular momentum and the inflow of material may weaken the bar, eventually causing it to dissolve. This transformation could lead to a more traditional spiral galaxy or even an elliptical form, depending on external influences such as mergers or interactions. Observing this barred titan provides astronomers with a snapshot of a galaxy in transition, offering clues about the long-term life cycles of barred spirals. This grand barred spiral, a cosmic symphony of light and motion, invites speculation about its future and the larger story of its role within the evolving universe. Like all galaxies, this one is not static. It is a living entity shaped by time, gravity, and its surrounding environment. While its current structure is dominated by the bold bar and sweeping spiral arms, its ultimate fate may look vastly different, offering tantalizing clues about how galaxies transform over cosmic timescales. In the far future, the bar at the galaxy's center, now a striking and dynamic feature, may begin to fade. Bars are not permanent, they are thought to evolve over billions of years, gradually dissolving as the redistribution of angular momentum reshapes the galaxy. As stars and gas migrate outward from the bar, its structure could weaken and give way to a more classical spiral shape. Alternatively, external influences such as interactions with nearby galaxies could accelerate this process, further disrupting the bar's stability and possibly triggering a major reorganization of the galaxy's structure. The spiral arms, too, are in constant motion, slowly changing as density waves move through them. Over time, as the gas supply dwindles, these arms may become less pronounced, fading into a more uniform disk. This would mark a significant shift in the galaxy's life cycle, as star formation slows and it transitions into a quieter, more stable phase. Such a future reflects the natural aging process of galaxies, where periods of intense activity eventually give way to calmer, less dynamic states. This galactic masterpiece is also part of a much larger narrative, the evolution of the universe itself. As the cosmos continues to expand, the space between galaxies grows, making interactions less frequent over immense timescales. However, for this barred spiral, its relative proximity to other galaxies means it may still experience gravitational encounters in the distant future. These encounters could lead to dramatic mergers, reshaping the galaxy entirely and forming a new, larger system. Such mergers are common in the universe and often lead to the formation of elliptical galaxies, giant, featureless structures dominated by older stars. At the galaxy's core, the presence of a supermassive black hole adds another layer of intrigue to its future. While currently dormant or relatively inactive, this black hole could awaken if enough gas and material are funneled into its vicinity. Such activity would transform the galaxy's nucleus into a quasar or active galactic nucleus, emitting intense radiation altering the surrounding environment. Even in its current state, the black hole subtly influences the motion of stars and gas near the core, acting as a gravitational anchor for the entire system. Beyond its internal evolution, this barred spiral is part of the cosmic web, a vast network of galaxies, clusters, and filaments that stretches across the universe. Its interactions with this larger structure provide insights into the role of individual galaxies in shaping the universe's overall architecture. For instance, the faint tidal streams and distorted features in its outer regions suggest past mergers or accretions, events that contribute to the growth of galaxies and the redistribution of matter on a cosmic scale. The study of this galactic wonder also raises questions about the long-term behavior of dark matter. Encased in an invisible halo of dark matter, this galaxy relies on this mysterious substance to maintain its structure and rotation. As our understanding of dark matter deepens, astronomers hope to uncover how these halos evolve and interact with the visible components of galaxies. This could lead to groundbreaking discoveries about the fundamental forces that govern the universe. Ultimately, this barred spiral is more than just a single galaxy. It is a window into the mechanisms that have shaped the cosmos for over 13 billion years. From the intricate dynamics of its bar and spiral arms to the hidden influences of dark matter and the potential of future mergers, every aspect of this galaxy tells a story of creation, transformation, and the ongoing dance of matter and energy in the universe. The deeper we dive into the story of this magnificent barred spiral galaxy, the more profound its connection to the cosmos becomes. Its role is not just that of an isolated star system, but as an active participant in the grand drama of universal evolution. From its bar and spiral arms to its hidden dark matter halo, each component is a piece of a larger puzzle that reveals the intricate relationships between matter, energy, and time. At the heart of this galaxy lies its most enigmatic and powerful feature, the supermassive black hole. Though it remains quiet now, it holds the potential to dramatically alter the galaxy's fate. If sufficient gas and dust are funneled into its gravitational pull, perhaps through a future galactic interaction, the black hole could erupt into activity, transforming the galaxy into a quasar. This phase would be marked by the release of intense jets of energy, capable of affecting star formation across the entire galaxy. Such phenomena highlight the incredible influence of these cosmic giants, even when their presence is invisible. The bar itself, a cosmic sculpture of structure and motion, is a temporary yet transformative feature. Studies of galaxies like this one suggest that bars are a middle chapter in the life story of spiral galaxies. They form when gravitational instabilities cause stars and gas to align into elongated shapes, redistributing angular momentum and creating the intricate patterns seen in the spiral arms. Over time, however, the bar may dissipate, leaving behind a more uniform disk. Observing this barred galaxy offers a snapshot of this transitional phase, revealing how galaxies shift between states over billions of years. One of the most fascinating aspects of this galactic masterpiece is its potential for future interactions. While it currently resides in a relatively quiet region of the universe, its gravitational pull ensures it remains connected to other galaxies in its vicinity. Future encounters with smaller galaxies or intergalactic clouds could trigger a cascade of changes, from bursts of star formation to the eventual merger of systems. Each interaction would add to the galaxy's mass and complexity, further enriching its already intricate structure. Even now, the outer edges of this spiral wonder bear the marks of its dynamic past. Faint tidal streams, barely visible against the darkness of space, suggest that this galaxy has absorbed smaller systems over time. These mergers, while subtle, are essential to the growth of galaxies, allowing them to accumulate stars, gas, and dark matter. These events leave behind not only structural scars but also a story of survival and adaptation, as the galaxy integrates these new components into its overall framework. This barred spiral's role in the larger cosmic web is another layer of its significance. As part of this interconnected network of galaxies and filaments, it contributes to the flow of matter and energy across the universe. Gravitational interactions between galaxies within this web help shape their evolution, guiding the formation of stars and the distribution of dark matter. This galaxy, like all others, is both an individual entity and part of a much larger system, illustrating the dual nature of the universe as both fragmented and unified. The interplay between visible and invisible matter in this galaxy is another profound mystery. Its luminous stars and glowing gas are merely the surface of its existence. Encased within a vast dark matter halo, this galaxy's structure and stability are deeply tied to forces we cannot see. Dark matter, though elusive, provides the gravitational framework for the galaxy's rotation and growth. Without it, the spiral arms and bar would not hold their shape, and the galaxy would collapse under its own motion. The future of this galactic titan, like all galaxies, is one of inevitable change. Over billions of years, its gas will be consumed or expelled, its star formation will slow, and its structure will shift. Whether it evolves into a more traditional spiral galaxy, merges into a larger system, or transitions into an elliptical galaxy depends on the complex interplay of internal dynamics and external forces. Each possible path offers new opportunities for discovery, as astronomers continue to piece together the life cycles of galaxies across the cosmos. This barred spiral galaxy is a reminder of the universe's ceaseless creativity. It is a snapshot of cosmic evolution, a living system in the midst of its journey through space and time. From its glowing core to its faint outer edges, every aspect of this galaxy tells a story of formation, transformation, and survival in a universe that is constantly in motion. This barred spiral galaxy, a masterpiece etched into the fabric of the cosmos, is more than a celestial object. It is a testament to the universe's infinite capacity for beauty and complexity. Its structure, from the radiant core to the farthest reaches of its spiral arms, is a symphony of creation, destruction, and rebirth that has played out for billions of years. To gaze upon it is to witness a story that stretches across eons, written in the language of stars, gas, and unseen forces. The spiral arms of this galactic wonder, like flowing rivers of starlight, are where some of the universe's most dramatic events unfold. Here, interstellar clouds of gas and dust are compressed by density waves, triggering the birth of stars in spectacular stellar nurseries. Massive, luminous stars emerge in these regions, their intense radiation sculpting the surrounding material into glowing nebulae. These stars live fast and die young, ending their lives in powerful supernova explosions that enrich the galaxy with heavy elements, the seeds for future stars, planets, and perhaps even life. At the galaxy's heart lies its luminous bar, a structure that defies the stillness of the cosmos. This bar is not a relic of the past but an active force, shaping the flow of matter and energy within the galaxy. It serves as a gravitational engine, driving gas inward toward the nucleus and outward into the spiral arms. This process fuels both the galaxy's core and its star-forming regions, creating a delicate balance that sustains its vibrant activity. The bar itself is a transient feature, a fleeting phase in the galaxy's life cycle that will one day fade, leaving behind a different form altogether. But the nucleus of this cosmic giant is where its mysteries deepen. Within the central regions, a supermassive black hole may reside, a silent titan whose gravitational pull shapes the motions of stars and gas in its vicinity. Though dormant now, this black hole holds the potential to awaken, unleashing jets of energy that could reshape the galaxy's inner structure. This hidden power at the core is a reminder of the duality of galaxies, places of creation and destruction, where light and shadow coexist in an eternal dance. Encasing the galaxy is its dark matter halo, an invisible scaffolding that provides the gravitational foundation for its existence. Dark matter, though unseen, is the silent architect of the universe, holding galaxies together and guiding their rotation. Without it, the galaxy's delicate spiral arms and bar would disintegrate, leaving chaos in their wake. Studying this hidden component offers a glimpse into the fundamental forces that govern the cosmos, bridging the gap between the known and the unknown. Beyond the galaxy itself lies the vastness of the cosmic web, a network of galaxies, clusters, and filaments that stretches across the universe. This barred spiral, though unique, is one node in this immense structure, its interactions with neighboring galaxies shaping both its destiny and that of the surrounding space. These interactions, whether through gentle gravitational pulls or dramatic mergers, leave imprints on the galaxy's structure, faint tidal streams, warped arms, or bursts of star formation that echo through time. In the far future, this galactic marvel will undergo profound transformations. As its gas reserves dwindle, star formation will slow, and its spiral arms may fade into a featureless disk. Its bar, once a bold centerpiece, will dissolve, and the galaxy may merge with others, becoming part of a larger system. These changes are not losses but transitions, as it continues its response to surround endless creativity, a living testament to the forces that shape and sustain the cosmos. Its luminous beauty, dynamic processes, and hidden mysteries remind us that the universe is not a static place but a realm of constant motion and transformation. Every observation of this celestial wonder adds another layer to its story, deepening our understanding of the universe and our place within it. This barred spiral galaxy, a cosmic masterpiece suspended in the vast darkness of space, is a reminder of the infinite wonders that unfold in the universe. Its existence speaks to the ceaseless power of gravity and time, shaping its structure, igniting its stars, and weaving its story into the grand narrative of the cosmos. It is not just a galaxy, it is a living, breathing tapestry of creation, bound by forces both visible and invisible. The spiral arms of this stellar titan, shimmering with clusters of newborn stars, stretch like luminous pathways through the cosmic void. These arms are home to some of the most dramatic events in the galaxy. In dense regions of interstellar gas and dust, gravity takes hold, collapsing clouds into fiery star-forming regions. Massive blue stars, brilliant and short-lived, emerge to illuminate their surroundings, their ultraviolet radiation carving glowing shapes into the nebulous material. These stars live their lives in the blink of an eye on cosmic scales, ending in explosive supernovae that scatter heavy elements into space. These elements, the building blocks of planets and life, are the galaxy's gift to the universe, a cosmic cycle of death and rebirth that echoes through time. Yet the galaxy's story is not only one of creation but also of dynamic motion. Its bar, a structure of immense scale, dominates the galaxy's core, acting as a gravitational bridge between the nucleus and its spiral arms. This bar is a cosmic engine, driving the flow of gas and dust inward toward the central regions. Here, the material collects in a nuclear ring, a glowing ring of star-forming activity that encircles the galactic heart. This ring, a hotspot of youthful stars and turbulent energy, represents the dynamic relationship between the bar's influence and the galaxy's natural cycles. Observing this process provides astronomers with a rare glimpse into how galaxies sustain themselves, balancing destruction and creation in a cosmic rhythm. Deep within the nucleus lies the galaxy's most enigmatic and powerful force, a supermassive black hole. Though invisible to the eye, its presence is felt in the motion of stars and gas that orbit near its event horizon. This black hole is a paradox, a region of ultimate darkness surrounded by the brightest regions of the galaxy. While dormant now, it holds the potential to awaken, transforming the galaxy into an active powerhouse, with jets of radiation capable of altering the structure and energy balance of its surroundings. This duality, of silence and fury, is a testament to the extremes of the universe. Beyond the galaxy's luminous features lies the silent, unseen hand of dark matter. This mysterious substance, which makes up the majority of the galaxy's mass, forms an invisible halo that stretches far beyond the visible spiral arms. Dark matter provides the gravitational framework for the galaxy's rotation, ensuring its outer regions do not spiral out into the void. Though it cannot be observed directly, its influence is undeniable, and its presence raises profound questions about the nature of the universe. What is dark matter? How did it come to shape the cosmos? These questions drive some of the most ambitious scientific inquiries of our time. The galaxy's story is also one of connection. It is not an isolated island in the universe but a part of the cosmic web, a vast network of galaxies linked by the force of gravity. This web, stretching across billions of light-years, connects galaxies in clusters, filaments, and voids, shaping the universe on the largest scales. The faint distortions in this galaxy's outer regions, tidal streams, warped arms, are the scars of past interactions with smaller galaxies. These encounters are reminders of the galaxy's dynamic history, moments of transformation that have added to its complexity and beauty. Looking to the future, the destiny of this barred spiral galaxy is one of inevitable change. Over billions of years, as its gas is consumed or expelled, its ability to form new stars will wane. The bar, a transient feature, will fade away, leaving behind a smoother, more uniform structure. The spiral arms may dissolve, their light dimming as the galaxy transitions into a quieter phase of existence. Eventually, it may merge with another galaxy, its identity blending into a larger system. This is the nature of the universe: change, adaptation, and renewal. But even as it evolves, this galaxy will remain a source of wonder and knowledge. Each observation reveals more about the forces that govern the universe, from the physics of star formation to the mysteries of dark matter. Its story is one of endless discovery, a reminder that the cosmos is as much about questions as it is about answers. This barred spiral galaxy is more than a celestial marvel, it is a riddle wrapped in light and shadow, a labyrinth of cosmic secrets waiting to be unraveled. Every facet of its existence holds a deeper truth, a clue to the forces that sculpt the universe. From its dazzling spiral arms to the unseen depths of its dark matter halo, it invites us to question everything we think we know about the cosmos. One of the most intriguing mysteries lies within the galaxy's bar, a structure that seems both permanent and transient, steady yet dynamic. Why do bars form in some galaxies and not in others? What cosmic hand decides whether a galaxy becomes a grand design spiral, a chaotic flocculent, or an unassuming elliptical? This bar, stretching tens of thousands of light-years, may hold the answer. Acting as a gravitational conveyor belt, it funnels gas inward while flinging stars outward, creating a balance of motion that appears almost deliberate. Yet this balance is fragile. A subtle nudge, a passing galaxy, a shift in dark matter, could send it spiraling into chaos. The core of the galaxy, shrouded in mystery, is a cosmic paradox. It is home to a supermassive black hole, a region where gravity is so intense that not even light can escape. And yet, surrounding this void is a nuclear ring teeming with life, massive stars being born, shining brilliantly for millions of years before dying in spectacular explosions. How can such a lifeless force coexist with such creation? This delicate interplay between destruction and birth raises profound questions about the nature of the universe itself. Is chaos necessary for creation? Is the galaxy's heart a mirror of the universe, where order and disorder dance together in perpetual harmony? Even the spiral arms, those iconic structures of beauty, are riddled with puzzles. These arms are not static, they are waves of density, rippling through the galaxy like cosmic tides. But what drives these waves? Are they the echoes of past galactic collisions, remnants of ancient gravitational encounters? Or are they self-sustaining phenomena, perpetuated by the stars and gas that flow through them? Within these arms, new stars are born, but not randomly. They seem to form in bursts, clustered together as if guided by an unseen hand. What governs this process? Could the influence of dark matter, hidden but ever-present, be the silent architect of these patterns? The galaxy's dark matter halo is perhaps its greatest enigma. This invisible cocoon, vast and unmeasurable directly, is the foundation of the galaxy's existence. Without it, the galaxy would fall apart, its stars and gas would drift into the void. Yet we know so little about dark matter, what it is, where it comes from, and why it behaves as it does. Does it hold the key to understanding the universe's origins? Is it the missing piece of a cosmic puzzle we have yet to fully grasp? As we study the rotation of this galaxy's stars, we are not just observing motion, we are decoding the fingerprints of a force that has shaped the universe since the beginning of time. And what of this galaxy's future? It is a titan now, a luminous giant in the cosmic night. But time spares no one, not even galaxies. Its bar will fade, its gas will run dry, and its spiral arms will grow faint. In billions of years, it may collide with a neighboring galaxy, their structures merging into a chaotic swirl before settling into a new form, perhaps an elliptical galaxy, quiet and subdued. Or it may end in isolation, drifting through an ever-expanding universe where stars burn out one by one, leaving behind only darkness. Yet even in its eventual demise, this galaxy's legacy will endure. The stars it forged, the elements it scattered, the planets it may have nurtured, all will become part of a greater cosmic story. Its matter will not disappear, it will be recycled, forming new stars, new galaxies, and perhaps even new life. This is the ultimate truth of the universe: nothing is lost, only transformed. This barred spiral is not just an object to observe, it is a question to ponder, a story to uncover, and a wonder to behold. Its existence reminds us that the universe is not static but alive with motion, change, and mystery. Every flicker of starlight, every ripple of gas, every hidden strand of dark matter is a clue, a whisper from the cosmos, inviting us to look deeper, think bigger, and dream farther. This barred spiral galaxy, a cosmic tapestry woven from light, shadow, and mystery, stands as a monument to the boundless creativity of the universe. Its story, written over billions of years, is one of ceaseless transformation, a cycle of creation, destruction, and renewal that mirrors the very essence of existence itself. As we study its luminous arms, its dynamic bar, and its hidden heart, we are not just observing an isolated star system, we are glimpsing the intricate interplay of forces that govern the cosmos. This galaxy reminds us that beauty and complexity arise from balance. Its structure, a harmonious blend of luminous stars, dark matter, and interstellar gas, exists because of an equilibrium between gravity, motion, and energy. The spiral arms, with their glowing star-forming regions, are the result of waves that propagate through the galaxy, compressing gas into dense, star-filled clouds. These arms are both ephemeral and enduring, constantly changing yet always maintaining their majestic shape, a testament to the galaxy's dynamic stability. The bar, a bold centerpiece that dominates its core, is a transient feature, destined to dissolve as the galaxy evolves. Yet, in its current form, it plays a pivotal role in shaping the galaxy's future. Acting as a cosmic engine, it directs gas and dust inward, fueling the nuclear ring, a hub of intense star formation and turbulent energy. This region, alive with the birth and death of massive stars, is a microcosm of the galaxy's larger cycles, a place where the forces of creation and destruction coexist in perfect balance. Deep within the core lies the galaxy's greatest enigma, a supermassive black hole. Silent and hidden, it exerts an invisible influence over its surroundings, anchoring the galaxy's nucleus and shaping the motion of nearby stars. Though dormant now, it holds the potential to awaken, unleashing jets of energy that could transform the galaxy's structure. Its presence is a reminder of the extremes of the universe, where ultimate darkness can coexist with brilliant light. Beyond its visible beauty, this galaxy is bound together by an invisible force, dark matter. This mysterious substance, forming an extensive halo around the galaxy, is the glue that holds its luminous components together. Without dark matter, the galaxy's stars and gas would drift apart, unable to sustain their rotation. This unseen component is not just a stabilizing force, it is a profound mystery that challenges our understanding of the universe. As we probe the motions of stars and gas, we are also uncovering the secrets of dark matter, piecing together the story of a force that has shaped the cosmos since its earliest moments. The galaxy's place in the cosmic web further underscores its interconnectedness. It is not an isolated island but part of a vast network of galaxies, clusters, and filaments that stretch across the universe. Its faint tidal streams and warped outer arms are evidence of past encounters, interactions with smaller galaxies that have left their marks on its structure. These encounters, though subtle, have shaped its evolution, adding mass, triggering star formation, and creating the patterns we observe today. But as majestic as this barred spiral is now, its future is one of transformation. Over billions of years, its gas reserves will deplete, and its star-forming activity will slow. The bar, a temporary feature, will dissolve, leaving behind a smoother, more uniform disk. The spiral arms may fade, their light dimming as the galaxy transitions into a quieter phase. It may merge with another galaxy, its identity blending into a new system, or drift in solitude through an ever-expanding universe. Whatever its fate, it will not be the end but a continuation, a new chapter in the story of the cosmos. This barred spiral galaxy is more than a celestial object, it is a reflection of the universe's endless cycles of change and creation. It reminds us that nothing in the cosmos is static, that every star, every structure, every ripple of gas and dark matter is part of a grander narrative. To observe it is to step into the mind of the universe itself, to marvel at the forces that shape not only galaxies but the very fabric of existence. In the end, this galaxy teaches us a profound truth: the universe is alive, not just with stars and galaxies but with stories, stories of how matter becomes light, how chaos becomes order, and how time weaves everything into the infinite tapestry of the cosmos. Its light, traveling across millions of light-years, is a message from the past, a whisper from the stars, inviting us to explore, to question, and to dream. It is a reminder that, as vast as the universe is, its mysteries are within reach, waiting to be uncovered by those who dare to look beyond the horizon. This galactic giant is not a static entity, it is part of the eternal cycle of cosmic evolution. The universe is not a still canvas but a dynamic space where galaxies are born, develop, interact, and ultimately change or fade away. Right now, this spiral system is in an active phase of star formation. Its arms are illuminated by young, massive stars, but astrophysical models predict that this period will not last forever. Over time, the processes regulating the birth of new stars will lead to a gradual decline in this activity. Star formation cannot continue indefinitely. The supply of cold gas, the raw material for new stars, will eventually be depleted. Cosmic winds and stellar explosions will expel much of this material into intergalactic space. The activity of the central black hole may also play a role, heating the surrounding gas and preventing it from collapsing into new stars. If no fresh gas flows in, the system will gradually enter a passive state where star birth ceases. The black hole at the galaxy's core is a key factor in determining its future. If it continues to consume matter, it may become even more active, releasing powerful jets of energy and creating shockwaves that alter the surrounding space. Such processes can either stimulate star formation or suppress it. If the surrounding gas is exhausted, the black hole will enter a dormant state, leaving behind only faint traces of X-ray radiation. This system does not exist in isolation. Nearby galaxies orbit around it, and there is a possibility that they will collide in the future. A merger could trigger a burst of star formation, but it could also destroy the ordered structure of the spiral arms, transforming the system into an elliptical form. Such events often lead to chaos in the internal dynamics of stellar orbits and fundamental changes in morphology. If this formation becomes part of a larger galactic cluster, the pressure from the surrounding environment may strip it of its remaining gas, completely shutting down star formation. In that case, it will become a fainter and more passive system where stars age without new generations replacing them. Observations suggest that this stellar island is surrounded by a vast dark matter halo. This invisible substance holds the galaxy together, preventing its stars from drifting apart. The question of how dark matter is distributed and what properties it possesses remains one of the greatest mysteries in modern astrophysics. Some theories suggest that dark matter consists of dense clumps, influencing the motion of stars and gas. Other hypotheses propose that dark matter interacts with itself in ways that we have yet to detect. Over time, the galaxy will become dominated by stars that have reached the end of their life cycles. White dwarfs, neutron stars, and black holes will gradually replace the younger, more luminous stars. If star formation ceases entirely, this world will, in trillions of years, become a place populated only by the faint remnants of once bright celestial bodies. Beyond internal factors, the system's fate will also be shaped by the evolution of the universe itself. The expansion of space is gradually increasing the distances between galaxies. If this process continues, then in the far future, surrounding objects may disappear beyond the cosmic event horizon, leaving this stellar world in complete isolation. The question of whether this galaxy could ever become home to intelligent life remains unanswered. If life arises within one of its planetary systems, it will encounter conditions different from those found in our own galaxy. In an era when bright stars fade, civilizations may search for ways to harness the energy of white dwarfs, neutron stars, or even black holes. Perhaps, in the distant future, advanced technologies will emerge that allow civilizations to manage energy resources on a galactic scale. This stellar world is one of countless objects in the universe, each a dynamic system evolving over time. Its fate could take many paths, retaining its current structure, transforming into an elliptical system, merging with other formations, or becoming isolated due to the expansion of the universe. But no matter what its final destiny may be, it remains part of the continuous cosmic process. Every star, every gas cloud, every gravitational force is a link in the great chain of the universe's evolution. We have only begun to uncover this story, and many discoveries still lie ahead. As observers continue to study distant galaxies, each new detail becomes part of an endless exploration that will never truly end. As time passes, this vast galactic structure will continue to change, shaped by both internal and external cosmic forces. While the present era is marked by active star formation, powerful stellar winds, and dynamic interactions, the distant future will bring a more gradual transformation. The balance between creation and destruction, between the birth of new stars and the fading of the old, will ultimately determine how this system evolves over billions or even trillions of years. The slow depletion of gas will lead to a decline in the birth of bright, massive stars. The spiral arms, once vibrant with nebulae and young stellar clusters, will begin to fade as fewer new stars form to replace those that die. The remaining gas will become increasingly diffuse, spread thinly across the galaxy, no longer able to collapse into dense clouds that fuel star formation. If no external gas flows in from intergalactic space, this system will slowly transition into a quieter, less active state. While the visible structure of the galaxy undergoes these changes, its invisible dark matter halo will continue to play a crucial role in its long-term evolution. The unseen gravitational framework that holds the stars and gas together may influence future mergers, interactions, and even the galaxy's eventual fate. Some theories suggest that dark matter halos are not static but may evolve over time, possibly affecting how galaxies like this one maintain their structure over cosmic timescales. As the number of new stars decreases, the population of stellar remnants will grow. White dwarfs will become the dominant stellar type, their faint glow persisting as they gradually cool over trillions of years. Neutron stars and black holes will also become more common, remnants of the most massive stars that once illuminated the galaxy. If enough black holes exist within the system, they may begin to interact gravitationally, forming dense clusters or even merging into larger structures that could eventually fall toward the central supermassive black hole. Over billions of years, the galaxy may undergo a transformation driven by gravitational interactions with other systems. If it merges with a neighboring galaxy, it may lose its spiral structure, becoming an elliptical system where stars move in more randomized orbits. Such a transition would mark a major shift in its evolutionary path, reshaping the way stars and stellar remnants are distributed throughout its volume. In a more extreme scenario, if the galaxy is absorbed into a massive galactic cluster, it may experience what is known as ram pressure stripping. This process occurs when a galaxy moves through the hot gas that fills the space between galaxies in a cluster. The pressure exerted by this intergalactic medium can strip away any remaining gas, effectively halting star formation entirely. This would leave behind a system composed mostly of aging stars, gradually fading over time. Beyond these local events, the larger-scale evolution of the universe itself will influence the ultimate fate of this galactic giant. The expansion of space, driven by dark energy, is accelerating. If this acceleration continues indefinitely, galaxies will become increasingly isolated, drifting apart until they can no longer interact with one another. Over time, this system may find itself alone in an expanding void, with no nearby galaxies left to merge with or draw gas from. In the far future, as the last remaining stars exhaust their nuclear fuel, the galaxy will enter its final stage. White dwarfs will continue to cool, becoming black dwarfs, cold, dark remnants emitting no light. Black holes will persist, slowly evaporating through Hawking radiation, though this process takes an unimaginably long time. Over an almost inconceivable timescale, the galaxy itself may become a vast, dark collection of degenerate matter, silent and unchanging. But even in this distant future, the story of this galaxy will not truly be over. The fundamental forces that shaped it, gravity, dark matter, cosmic expansion, will continue to operate. New discoveries may one day reveal unknown processes that influence its fate in ways we cannot yet predict. Perhaps advanced civilizations, if they arise and endure, will find ways to manipulate stellar remnants, harnessing the energy of neutron stars or even black holes to sustain life long after ordinary stars have burned out. For now, this galaxy remains a vibrant and active system, a luminous beacon in the cosmos. Its arms swirl with gas and dust, its stars shine brightly, and its core harbors the powerful force of a supermassive black hole. It is a system still in motion, still evolving, still participating in the grand, ongoing story of the universe. And as we continue to observe it, to study its mysteries and map its future, we are reminded that the universe itself is not static. Every galaxy, every star, every atom is part of an endless cosmic dance, a process of change and transformation that spans across time and space. This galaxy's story is far from over. It is just one chapter in the ever-unfolding narrative of the cosmos, a reminder that, in the vastness of the universe, there is always more to discover. As the cosmic clock continues to advance, the evolution of this galactic titan will be shaped by forces both predictable and mysterious. While the structure we observe today is vibrant and full of energy, the deeper laws governing the universe ensure that no celestial body remains unchanged. Over unimaginable timescales, this stellar system will transition through different phases, each marking a new chapter in its vast history. The present moment, defined by the ongoing formation of stars, will eventually give way to a quieter era. The great nebulae that now serve as stellar nurseries will slowly disperse, leaving behind only the stars that have already formed. Without a steady influx of cold gas, no new generations will emerge to replace those that burn out. This decline will be gradual at first, barely perceptible over human lifetimes, but over billions of years, the difference will become clear. The galaxy's arms will fade, the glow of massive blue stars will disappear, and only long-lived red dwarfs and cooling remnants will remain. While the visible features of the galaxy change, unseen processes will continue to influence its fate. The dark matter halo surrounding the system will persist as a gravitational scaffold, shaping the movement of its stars even after the loss of its brightest members. Some theories suggest that interactions within dark matter halos could lead to subtle, long-term effects on galactic evolution, possibly altering the way stars orbit or influencing future mergers in ways not yet fully understood. Even as the galaxy settles into a more passive state, the remnants of its former brilliance will still be present. White dwarfs will form a vast population, each a dimming ember of a once luminous star. Neutron stars, the collapsed cores of the most massive stars, will rotate silently, some still emitting faint pulses of radiation. Black holes, formed from the deaths of the heaviest stars, will drift through the system, invisible but ever-present, exerting their gravitational influence. The central supermassive black hole, now dormant or only occasionally active, will remain as the galaxy's silent core. Over time, it may continue to gain mass through slow accretion or by merging with other black holes, should galactic interactions bring new material into its reach. If the system experiences a major merger, this black hole could awaken once more, unleashing powerful jets of energy that briefly reshape its surroundings before fading into darkness again. The long-term fate of the galaxy is also bound to the broader evolution of the universe itself. If cosmic expansion continues at its current accelerating rate, galaxies will drift further apart, severing their connections to the larger structures they once belonged to. Eventually, even the faintest traces of other galaxies will recede beyond the observable horizon, leaving this system alone in an increasingly empty cosmos. Without new interactions to provide fresh material, it will continue its slow transition into darkness. In the deepest future, when trillions of years have passed, even the longest-lived stars will begin to fade. Red dwarfs, which burn their fuel with extreme efficiency, will eventually exhaust their reserves, leaving behind a universe filled only with cooling remnants. The galaxy will become a place of silent white dwarfs, non-rotating neutron stars, and black holes, drifting endlessly through the void. Even these objects, given enough time, may meet their end. White dwarfs will cool to black dwarfs, emitting no heat or light. Black holes, the most enduring structures of all, may slowly evaporate through the slow process of Hawking radiation, vanishing into the vacuum of space. Yet despite this seemingly inevitable decline, the universe remains a place of possibility. If advanced civilizations arise within the galaxy's lifespan, they may develop ways to harness the energy of its remnants, finding new methods of survival long after the stars have faded. Technologies beyond our current imagination may allow life to persist, adapting to the cold, dark universe that will one day emerge. For now, however, this galaxy remains alive, its stars burning brightly, its spiral arms stretching across space, its black hole holding court at the center of a vast and complex system. It is a place of ongoing transformation, where cosmic forces play out on scales both vast and intricate. Every supernova, every drifting planet, every magnetic field tells a story written in the language of the cosmos. As we continue to study it, we are reminded that the universe itself is never static. It is an ever-changing tapestry of matter, energy, and space-time, each moment leading to the next in an infinite sequence of events. This galaxy's journey is far from over, it is simply part of the grand, continuous motion of the cosmos. And as long as there are observers to look toward the stars, its story will continue to unfold, written across the fabric of time itself. The journey of this galaxy through the cosmic expanse continues, an unceasing progression through the vast, uncharted reaches of time. While its present form is defined by swirling arms of stars, luminous nebulae, and a dynamic interplay of stellar forces, the distant future will see it undergo transformations that stretch beyond the scope of current understanding. Each stage in its evolution is part of a grander cycle, where birth, growth, and decay are inextricably linked. Even as the light of new stars fades, the underlying gravitational structures will endure. The stars that once illuminated the galaxy will drift through a steadily dimming sky, bound to their orbits by the unseen mass of dark matter. Over eons, these orbits may shift due to subtle gravitational interactions, causing some stars to migrate outward while others spiral inward toward the central black hole. In some regions, dense stellar remnants may cluster, forming compact systems of white dwarfs, neutron stars, and black holes locked in a slow gravitational dance. While large-scale interactions will become increasingly rare as the universe expands, this does not mean the galaxy will remain entirely isolated from cosmic events. Rogue objects, free-floating planets, interstellar debris, or even intergalactic stars ejected from distant collisions, may pass through its boundaries, altering local dynamics in unexpected ways. Occasionally, binary systems may undergo disruptions, flinging one star outward at immense speeds while the other falls into the depths of a black hole. These rare events will provide brief but dramatic moments in an otherwise long, gradual shift toward equilibrium. At the heart of it all, the central black hole will persist as the galaxy's gravitational anchor, long after its brightest stars have faded. If no further matter is available to feed it, it may remain dormant, a dark monolith at the center of a dying system. Yet in the event of a galactic merger, even in the distant future, it could awaken once more, consuming stellar material and releasing vast amounts of energy in a final display of activity before the universe grows too empty to sustain such processes. On the longest timescales, when even the most enduring stars have faded into obscurity, the galaxy will be reduced to a vast collection of stellar remnants. White dwarfs, once the glowing cores of sun-like stars, will cool until they no longer emit any heat or light. Neutron stars, relics of past supernovae, will persist as silent, invisible spheres of dense matter. Black holes, the ultimate endpoints of stellar collapse, will remain scattered across the galactic remnant, their presence detectable only through their gravitational influence. Yet even black holes are not eternal. The slow process of Hawking radiation, a quantum effect predicted by theoretical physics, will cause them to lose mass over unimaginable timescales. As the final stages of the universe unfold, these black holes will gradually evaporate, releasing their remaining energy into the darkness. Eventually, after a period so long it defies human comprehension, the last traces of what was once a grand and thriving galaxy will dissipate, leaving behind nothing but the vast, empty expanse of space. But even in this apparent finality, the story of the universe itself may not be over. Some theories suggest that new physical processes could emerge in the distant future, leading to the birth of entirely new structures, new galaxies, or even new forms of matter and energy. The eventual fate of the cosmos remains one of the greatest mysteries, one that extends beyond even the long arc of this galaxy's existence. For now, this stellar system remains an active, vibrant participant in the ongoing story of the cosmos. Its stars still shine, its nebulae still swirl with potential, and its future remains unwritten. Whether it eventually fades into isolation, merges with another galactic system, or becomes the cradle of new cosmic phenomena, it is a reminder that the universe is not static, it is an ever-changing expanse of creation, transformation, and mystery. The galaxy's journey, like the universe itself, is one of constant motion. And as long as observers exist to study it, to trace its evolution, and to uncover the forces that shape it, its story will continue, woven into the grand tapestry of existence, a testament to the boundless nature of the cosmos. The passage of time within this galaxy, like that of all cosmic structures, is dictated by forces both seen and unseen. For now, it remains a place of light, energy, and movement, a system still brimming with stellar activity in the subtle interplay of gravity, radiation, and magnetic fields. Yet the deeper laws of physics ensure that change is inevitable. The stars that shine today will one day burn out, their remnants drifting through space, forming the silent foundation of a future where darkness and cold dominate. Even in the near future, on a galactic scale, this system will begin to experience noticeable shifts. The rate of new star formation will decline as available gas reservoirs dwindle, and stellar winds, supernovae, and active galactic feedback continue to expel material into intergalactic space. The most massive stars, those that once defined the brilliance of the galaxy's spiral arms, will be the first to vanish, leaving behind a less dynamic but still evolving stellar population. As the era of new stars comes to a close, the dominant sources of energy within the galaxy will change. While today it is driven by the nuclear fusion of young, luminous stars, in the future, much of its energy output will come from compact remnants, white dwarfs, neutron stars, and black holes. These objects, relics of past stellar generations, will continue to interact in gravitationally complex ways, forming dense stellar clusters where unusual astrophysical phenomena may emerge. With no new material to sustain star formation, the galaxy will enter a state of slow structural decay. The spiral arms, once teeming with brilliant clusters of hot, young stars, will become more diffuse and less distinct. The central regions, dominated by older stars, will gradually take on a more elliptical shape, as stellar orbits become increasingly randomized due to long-term gravitational interactions. If the system does not experience another major merger, it may retain much of its spiral character for an extended period, but eventually, it will lose the energy that sustains its grand structure. The presence of dark matter, though invisible, will continue to shape the motion of stars and stellar remnants. This unseen mass, concentrated in a vast halo extending far beyond the visible edges of the galaxy, will ensure that its overall gravitational integrity remains intact, even as individual stars come and go. Yet as time stretches onward, the exact nature of dark matter's influence remains uncertain. If dark matter interacts with itself or decays over cosmological timescales, it could subtly alter the galaxy's evolution in ways not yet fully understood. Far in the future, black holes will become the dominant gravitational players within the system. The central supermassive black hole, now a relatively quiet presence, may awaken if a late-stage galactic collision provides it with new material to consume. However, if no such event occurs, it will continue to exist in relative dormancy, exerting its pull on the remaining stars and stellar corpses that orbit its dark center. Meanwhile, smaller black holes, formed from the collapse of once massive stars, will roam the galaxy, occasionally merging and releasing bursts of gravitational waves that ripple through the fabric of spacetime. The next phase in the galaxy's life will be dominated by slow stellar dimming and cooling. The white dwarfs left behind by sun-like stars will take trillions of years to cool to black dwarfs, their faint infrared glow gradually fading into total darkness. The neutron stars, though more stable, will also lose energy over immense timescales, their once powerful magnetic fields dissipating until they become featureless, dense remnants. In the most distant future, when even these last stellar remnants have faded, the galaxy will be reduced to a vast, dark cloud of compact objects. White dwarfs will have long since cooled beyond detectability, neutron stars will have settled into silent motion, and the remaining black holes will be the only significant sources of gravitational influence. The occasional gravitational interactions between these objects may eject some of them into intergalactic space, while others may slowly spiral inward toward the supermassive black hole at the center. Even black holes are not eternal. If the theories of Hawking radiation hold true, over an unimaginable number of years, they will slowly evaporate, emitting minuscule amounts of radiation until they finally vanish. In the final stages, the last remaining structures of the galaxy will disappear entirely, leaving nothing but the expanding void. Yet even in this apparent finality, the larger fate of the universe remains unknown. Some cosmological theories suggest that new physics could emerge at extreme timescales, allowing for the rebirth of matter, the formation of new energy structures, or even the possibility of an entirely new phase of existence. Other models suggest that the universe will continue expanding indefinitely, growing colder and more desolate as entropy reaches its maximum. But for now, this galaxy is still very much alive. It is a place where stars are born and die, where black holes lurk in the shadows, and where gas clouds drift between the stars, waiting to be pulled together into new systems. It is still undergoing change, still writing its story in the language of light and gravity. And as long as there are eyes to observe it, whether human or some other intelligence that may one day rise within its countless stars, its journey through time will remain an inspiration. It is a reminder that the universe is not a static void but an evolving, dynamic entity, filled with forces beyond our comprehension, shaping worlds beyond our reach. This galaxy's tale is far from over. It is but one part of a far greater cosmic narrative, one that stretches across the depths of space and the boundless reaches of time. And as long as the universe itself exists, the echoes of its existence, its transformations, and its mysteries will endure, woven into the grand and infinite fabric of the cosmos. The journey of this galaxy is a testament to the ever-changing nature of the cosmos, where time, gravity, and energy weave an unbroken narrative of transformation. Even as it moves toward a quieter, less dynamic state, the fundamental forces that shaped it continue to operate, ensuring that its evolution, though gradual, will never truly cease. As the last great bursts of star formation fade, the galaxy will settle into a state of equilibrium, where the remaining stars age and cool without the replenishment of new stellar generations. The once vibrant interplay between young blue giants and glowing nebulae will be replaced by an increasing dominance of red and orange stars, those that burn their fuel slowly and persist long after the more massive stars have perished. Over time, even these long-lived dwarfs will begin to disappear, leaving behind a sky populated mostly by stellar remnants, silent echoes of a once thriving system. Though large-scale star formation will have ceased, cosmic interactions will continue on smaller scales. Gravitational encounters between stellar remnants may lead to occasional mergers, where white dwarfs collide to produce faint, short-lived bursts of energy. Some neutron stars, locked in decaying orbits around one another, may spiral inward over the course of eons, unleashing powerful gravitational waves in their final moments before merging into a single, ultra-dense object. These events, though rare, will be among the last luminous displays in the galaxy's history, marking the remnants of processes that once fueled its brilliance. At the heart of the system, the supermassive black hole will remain the most dominant force, exerting its influence over whatever matter still orbits its deep gravitational well. If no new gas is available for accretion, it will exist in a state of quiet solitude, an immense but invisible presence that once governed the flow of material at the galactic core. However, should future interactions send new objects toward it, whether wandering stars, smaller black holes, or the remnants of galactic mergers, it may still flare to life in brief, final outbursts of radiation before returning to dormancy. Beyond the slow transformations within the galaxy itself, the broader cosmic landscape will undergo equally profound shifts. The expansion of the universe, driven by dark energy, will continue stretching the fabric of space, increasing the distances between galaxies. If current models hold true, this system will one day be so far removed from its nearest neighbors that no light from them will ever reach it again. It will exist in solitude, drifting in an ever-expanding void, separated from any potential sources of new energy or interaction. In this distant future, even the most enduring stars will fade. The red dwarfs, which burn their hydrogen reserves with remarkable efficiency, will eventually deplete their fuel, transitioning into dim, cooling husks. White dwarfs, scattered throughout the galaxy, will continue their slow cooling process, radiating away their last traces of heat until they become black dwarfs, invisible and undetectable, existing only as faint gravitational imprints in the darkness. The galaxy, once a brilliant collection of spiraling stars and nebulae, will become a quiet graveyard of matter, a system of dead stars, black holes, and unseen remnants, orbiting in patterns set long ago but no longer changing. The gravitational pull that once held it together will remain, but without active energy sources, it will simply persist as a vast structure of cold, inactive objects, bound by forces that no longer shape new formations. But even these lingering remnants will not endure forever. If Hawking radiation is correct, then over unimaginable spans of time, even the black holes that dominate the galaxy's final phase will slowly evaporate, radiating away their mass particle by particle until nothing remains. The last trace of structure within this system, indeed, within any system, will be erased as even these cosmic titans fade into nothingness. At this stage, the universe itself may have reached what is theorized as the heat death, a state where entropy has maximized, all available energy has been evenly distributed, and no further work can be done. The last remaining particles will drift aimlessly in a sea of darkness, with no stars to shine, no forces to bind them together, and no structure left to shape the cosmos. And yet, even in this seemingly final state, mysteries remain. Some theories propose that at extreme timescales, new physics may emerge, allowing for the spontaneous formation of quantum fluctuations that could give rise to entirely new structures, perhaps even a new universe. Others suggest that unknown forces, beyond current understanding, could initiate a cosmic rebirth, resetting the universe into a new cycle of expansion, contraction, and formation. For now, however, this galaxy remains a place of light, energy, and motion. It is still home to stars, to planetary systems, and to forces that shape the cosmos on scales both vast and intricate. It is still evolving, still transforming, still existing as part of the grand, ever-unfolding story of the universe. And as long as there are minds to observe it, whether human or some future intelligence that may one day rise within its stars, its journey will not be forgotten. It will stand as a testament to the vastness of time, the relentless power of cosmic forces, and the mystery of existence itself. Even in the face of inevitable entropy, even in the depths of the farthest future, the legacy of this galaxy, its cycles of formation, its celestial dance, its silent end, will remain woven into the fabric of the cosmos, a whisper in the endless symphony of space and time. Even as the inevitable march of entropy dictates the distant fate of this galaxy, its existence, past, present, and future, remains a crucial part of the larger cosmic narrative. While its stars will one day fade, while its spiral arms will dissolve into a formless collection of stellar remnants, and while even its black holes will eventually disappear, it is not a mere passive participant in this grand story. Every collision, every burst of star formation, every gravitational interaction it has ever undergone has contributed to shaping the vast, evolving tapestry of the universe itself. For now, it is still a place of motion, where stars drift along their ancient orbits, where remnants of once massive suns cool in the silence of space, and where the invisible forces of dark matter still hold it together. The fabric of space-time bends subtly around its remaining black holes, the last gravitational wells marking where brilliant clusters of stars once illuminated the cosmic night. Even as star formation ceases, interactions between stellar remnants will continue. Binary white dwarfs may occasionally merge, igniting in final supernovae that momentarily rekindle some of the brightness lost over eons. Some neutron stars may collide, releasing bursts of gamma radiation that flash across space before vanishing into the abyss. These events will become rarer and rarer as time stretches forward, their light appearing like distant echoes of an era that once flourished. If a cosmic traveler, a future intelligence from a civilization born on one of this galaxy's planets, were to witness its slow transformation, they would see it as a system settling into a quiet, eternal slumber. The intricate balance of forces that once gave rise to its grand structure will dissolve, leaving behind a ghost of what once was. The beautiful, swirling motion of its spiral arms will be nothing but a memory written in the positions of long-cooled stellar remnants, their orbits preserving the shape of the past long after the light has faded. And yet, even in this state of near-total stillness, the galaxy will continue to move. It will drift through the expanding universe, carrying with it the remnants of countless past generations of stars, planets, and possibly even life that once arose in its systems. Every star that has ever shone, every world that has ever formed, every cosmic event that has ever unfolded within its boundaries has left a mark upon the larger fabric of reality. But what lies beyond the end? Some theories suggest that as the expansion of the universe accelerates, structures like this galaxy will become increasingly isolated, eventually disappearing beyond the event horizons of one another. This would mean that, in the deepest future, nothing from the outside universe would be able to reach this lone stellar graveyard. It would exist in complete solitude, no longer connected to the broader cosmic web from which it once drew its material and energy. Yet other possibilities remain open. There are theories that hint at the idea of cosmic rebirth, suggesting that fundamental forces may shift over unimaginable timescales, triggering a new phase of universal evolution. Perhaps the very fabric of space-time will undergo a transformation, giving rise to new structures, new energies, or even entirely new forms of matter. Could something rise from the ashes of this long silent galaxy, reshaping its cold remnants into the seeds of another universe? Or perhaps, if there is intelligence capable of enduring across such timescales, this galaxy may not remain a passive relic of the past but instead a domain of cosmic engineering. If civilizations survive the death of their stars, could they find ways to reignite new suns? Could they harness the gravitational energy of black holes to create new sources of warmth and light? Could they defy the seemingly inevitable fate of entropy, bending the rules of nature to construct a new age of stellar activity? For now, such questions remain beyond our reach. What is certain, however, is that the universe is not a static entity, nor has it ever been. From the moment of its birth, it has been in constant flux, each stage leading into the next, each transition reshaping the fate of galaxies, stars, and worlds. This galaxy's story, though it may seem to end in silence, is not a tragedy. It is a story of cycles, transformations, and endurance. It is a reminder that even in the face of entropy, in the face of an ever-expanding cosmos, there is meaning in the motions of celestial bodies, in the interactions of cosmic forces, in the rise and fall of stellar systems. It is not just a fading structure in an ancient universe, it is a link in a chain that stretches from the distant past into the unknowable future. It is a testament to the grand forces that govern reality, a cosmic echo that will resonate across time. And as long as there are observers, whether human or otherwise, to look toward the stars, to seek understanding, to marvel at the scale of existence, then the story of this galaxy will never truly be over. It will live on in the minds that remember it, in the equations that describe it, and in the unbroken continuum of the universe itself, a whisper in the void, a trace in the infinite, a mark upon eternity. Even in the farthest reaches of time, when the last embers of this galaxy have faded and its structure has dissolved into the silent drift of stellar remnants, its existence will remain woven into the fabric of the universe. The forces that shaped it, the stars that once illuminated its spiral arms, and the events that unfolded within its vast expanse have left an imprint upon reality itself. Though no longer a place of brilliant star clusters and luminous nebulae, it will not be forgotten by the cosmos. The energy that once flowed through its stars has been dispersed, the elements forged in their nuclear furnaces scattered across the void, now part of an unseen legacy stretching far beyond its borders. The gravitational ripples from ancient collisions still echo through spacetime, faint but real, inscribed into the very structure of the universe. In a universe where time stretches infinitely forward, the galaxy's past is not erased but absorbed into the grand continuity of existence. Every burst of stellar radiation, every gravitational interaction, every moment of transformation has contributed to shaping the cosmos as it is now, and as it will be in the future. Yet if the universe itself has an ultimate fate, if the expansion continues to accelerate, or if new physics emerges beyond our understanding, then even the idea of permanence may be an illusion. If dark energy persists, this galaxy will be carried ever outward, away from all others, lost in a cold and empty expanse where no new interactions can take place. In such a future, its remnants will continue their endless drift, untouched, unseen, unknowable to anything that might still exist elsewhere. But if the universe is cyclic, if there is a deeper pattern beyond the present expansion, then perhaps this is not the true end. Some theories suggest that the cosmos may one day contract, reversing its expansion and pulling everything back toward a new singularity, a rebirth where all past matter and energy are reshaped into the foundation of a new reality. If such a fate awaits, then this galaxy, though long dissolved, may become part of the material that fuels the birth of new stars, new galaxies, new structures beyond imagining. And even if the cosmos remains in perpetual expansion, with entropy driving it toward darkness, there may yet be unseen forces at play. Perhaps deep in the void, unknown mechanisms could reignite cosmic processes, birthing new structures in ways we cannot yet comprehend. Could remnants of this galaxy, scattered and cold, find new purpose in an epoch where the laws of physics themselves change? If intelligence endures, if civilizations, whether from this galaxy or another, find ways to persist beyond the deaths of their stars, then the knowledge of what once was will not vanish. Records of this galaxy's past may be preserved, its structure mapped, its evolution studied by minds that have transcended ordinary limitations of time and entropy. The image of its grand spiral form, long since unraveled, may still exist in archives that survive beyond stars, beyond black holes, beyond even the last remnants of ordinary matter. For now, this galaxy still turns, still shines, still plays its role in the vast cosmic dance. Its stars are not yet gone, its remnants not yet scattered to the cold depths of time. And as long as it exists, as long as light still escapes from its distant reaches, its presence in the universe remains undeniable. And even when its last light has faded, when its black holes have evaporated, when every particle has drifted into the background radiation of a silent cosmos, its existence will not have been in vain. It has been a part of something far greater, a universe where time does not erase but instead transforms, where energy does not disappear but shifts into new forms, where every celestial body, no matter how fleeting in the grand scale of eternity, contributes to the larger unfolding of reality. This galaxy's story may end in darkness, but it does not end in nothingness. It remains, always, a chapter in the infinite book of the cosmos, its essence forever imprinted upon the grand and unending tapestry of space and time. Even in the depths of an aging universe, where darkness slowly claims what once shone brightly, the essence of this galaxy fade, its dissolve, and its energy may vastness but upon the remains. Every atom, every photon, every gravitational wave that ever emanated from this system is now part of something greater. The elements forged in its stellar cores have traveled far beyond its borders, carried by supernovae, stellar winds, and intergalactic currents to become part of new worlds, new structures, perhaps even new life. Though its own light may no longer shine, the echoes of its existence persist in ways beyond our current comprehension. If there are still observers, beings capable of witnessing the slow unraveling of the cosmos, they may look upon this galaxy not as a relic, but as a monument to the vast interplay of forces that have governed the universe since its birth. To them, it may serve as a record of everything that has come before, a cosmic archive written not in books but in the arrangement of dead stars, in the subtle distortions of spacetime left by its long-past inhabitants. Perhaps, in the farthest reaches of time, intelligence will still endure, outlasting even the stars themselves. If such minds exist, they may develop ways to resist the pull of entropy, to construct new energy sources in the wake of a dying universe. Perhaps they will find remnants of galaxies like this one, gathering their scattered pieces to forge something new in a universe that no longer creates but only erases.